Hello and welcome back. I'm glad you're here. Maybe you had a long day. Maybe your mind is still racing with thoughts that won't quite settle, like leaves caught in an autumn wind. That's okay. Tonight, we're going to let those thoughts drift away, one by one, as we turn our attention outward, toward the cosmos, toward the infinite dark, toward mysteries so vast and beautiful that our everyday worries seem to dissolve in comparison. Tonight's journey takes us through 100 fascinating facts about space. Not the kind of facts that jolt you awake with alarm, but the kind that invite you to wonder, to contemplate, to let your imagination float gently like a dandelion seed on a summer breeze. We'll explore planets and stars, galaxies and nebulae, mysteries solved, and mysteries that remain tantalizingly just beyond our reach. Before we begin, if you enjoy these journeys through the cosmos, if they help you find that quiet place where sleep comes naturally, consider subscribing. It helps this channel continue creating these peaceful explorations, and it means we can keep wandering together through the wonders of science and space. Now let your body sink a little deeper into wherever you're resting. Let your breathing slow. There's nowhere you need to be, nothing you need to do. Just listen and let the universe unfold around you. Now let's begin. There's something delightfully strange about Venus. Among all the worlds in our solar system, it's the rebel, the one that decided to do things differently. You see, Venus rotates so slowly that a single day on Venus, one complete spin on its axis, actually lasts longer than an entire year on Venus. Let that settle in your mind for a moment. A day that's longer than a year. Here's what that means in numbers, though numbers themselves feel almost too precise for something so wonderfully absurd. Venus takes 243 Earth days to rotate once. Meanwhile, it only takes 225 Earth days for Venus to complete one orbit around the Sun. So if you were standing on the surface of Venus, not that you could, with its crushing atmospheric pressure and temperatures hot enough to melt lead, but if you could, you'd experience a sunrise. Watch the sun crawl across the sky, see it set, and then have to wait through more than a full Venusian year before you'd see it rise again. Time works differently there. It's a place where our ordinary intuitions about how days and years should relate to each other simply collapse. Perhaps Venus is teaching us something about the arbitrary nature of time itself. How we measure it, how we experience it, how it's really just our planet spinning and orbiting, and other worlds are free to dance to entirely different rhythms. On Venus, time moves like honey, thick and slow and strange. In July of 1969, Neil Armstrong pressed his boot into the lunar dust and created a footprint. That footprint is still there. And here's the beautiful, haunting part. It will likely remain there for millions of years, undisturbed, unchanged, a human mark on an inhuman world. The moon has no atmosphere, no wind to scatter the dust, no rain to wash it away, no weather of any kind. There's only silence and stillness, and the occasional micrometeorite impact. Those footprints from the Apollo missions, from Armstrong and Aldrin, from the later missions, from all 12 humans who walked on that gray dust, they're all still there, perfectly preserved. They're accidental time capsules, unintentional monuments to human curiosity and courage. Imagine that. 55 years from now, 100 years, 1,000 years, those footprints will still be there, testament to the day we first left our world to walk on another. They'll outlast most of what we build here on Earth. Buildings crumble, monuments erode, even mountains eventually wear down. But on the moon, in that airless quiet, our footprints will remain, perhaps long after we're gone, perhaps to be discovered one day by someone else, some other curious creatures wondering who walked here and why. It's humbling in a way, and also deeply moving. We were there, we touched another world, and the universe remembers. Saturn's rings are one of the most beautiful sights in the solar system. Through even a small telescope, they're breathtaking. Those elegant bands encircling the planet like a cosmic halo. But here's something that seems almost impossible. While Saturn's rings stretch 280,000 kilometers wide, they're mostly less than 1 kilometer thick. In some places, they're only about 10 meters thick. That's the height of a 3-story building. Think about that ratio for a moment. If you were to build a scale model where the rings were as thin as a sheet of paper, let's say 0.1 millimeters thick, those rings would stretch about 60 meters across, the length of a football field, but as thin as paper. It's a structure so delicate, so impossibly flat, that it almost defies imagination. And what are these rings made of? Mostly water ice. Billions upon billions of particles, ranging in size from tiny grains like sugar to massive chunks the size of houses, all orbiting Saturn in an impossibly thin plane. Some scientists think the rings might be relatively young, perhaps only a few 100 million years old, created when a moon wandered too close and was torn apart by Saturn's gravity. Others believe they could be ancient remnants from the solar system's formation. Either way, they're temporary. Gradually, inexorably, Saturn's gravity is pulling the ring material down into the planet itself. In perhaps 100 million years, the rings might be gone entirely. So we're lucky, in a cosmic sense, to live in an era when Saturn wears its crown. At Saturn's North Pole, there's a storm. But this isn't just any storm. It's shaped like a perfect hexagon. 6 straight sides, 6 angles, spinning around the pole like some kind of cosmic geometric puzzle. Each side of this hexagon is wider than Earth itself. And it's been there for decades, probably much longer, maintaining its bizarre shape through forces we still don't fully understand. When the Voyager spacecraft first spotted it in the 1980s, scientists were baffled. Storms on Earth are circular. Hurricanes, typhoons, they all spiral in rounded patterns. But this was different. The Cassini spacecraft later confirmed it, captured images of it, even saw it change color from bluish to golden as Saturn's seasons shifted. But that hexagonal shape, it remains. The leading theory involves something called Rossby waves, the same kind of atmospheric waves that create meandering patterns in Earth's jet streams. But to create such a stable, geometric shape requires a delicate balance of wind speeds, temperatures, and planetary rotation that we're only beginning to understand. It's as if Saturn decided to remind us that the universe isn't obligated to make sense in familiar ways. There's something almost artistic about it, don't you think? A planet painting geometric patterns in its own atmosphere, maintaining them for decades or centuries. A cosmic artwork that nobody was meant to see until we developed the technology to look closely enough. The universe is full of such hidden wonders, waiting patiently for us to notice them. Jupiter's Great Red Spot has been swirling for at least 350 years. Think about that timeline. When astronomers first pointed their primitive telescopes at Jupiter in the 1600s, that storm was already there, already ancient. It was there during the Enlightenment, during the Industrial Revolution, during both world wars, during the Apollo missions. It's been there for the entire span of modern science, and it shows no signs of stopping. It's a storm larger than Earth itself. Though it's been shrinking in recent years, it's still enormous by any reasonable measure. Wind speeds reach up to 400 kilometers per hour at its edges. And unlike hurricanes on Earth, which draw their energy from warm ocean water and quickly dissipate over land, Jupiter's great red spot has no land to slow it down, no solid surface at all. It just keeps spinning, fed by Jupiter's internal heat and the churning dynamics of its thick atmosphere. What must it be like inside that storm? We can only imagine. Lightning flashes that would dwarf anything on Earth. Clouds of ammonia, ice, and other exotic compounds. Temperatures and pressures that shift wildly as you move up and down through the atmospheric layers. It's a world unto itself, that storm. An entire weather system that's persisted longer than some civilizations. And here's the humbling part. It was already old when we first saw it. It might have been swirling for 1,000 years, or 10,000. We simply don't know. We only know that it's there, it's enduring, and it reminds us that the universe operates on time scales that make our human lifespans seem like brief candle flickers in an endless night. Mercury is the closest planet to the Sun, and you might think that makes it consistently, uniformly hot. But the reality is far stranger. During Mercury's day, which lasts 176 Earth days, the side facing the Sun heats up to about 430 degrees Celsius, hot enough to melt lead, hot enough to melt zinc. But then night falls, and because Mercury has almost no atmosphere to trap heat, the temperature plummets to negative 180 degrees Celsius. That's a 6 on 10 degree temperature shift between day and night. The most extreme temperature swing of any planet in our solar system. From melting metal to freezing cold in the span of one rotation. It's as if Mercury can't decide whether it wants to be an oven or a freezer, so it becomes both, swinging wildly between the two extremes. Why such a dramatic shift? It all comes down to atmosphere, or the lack of it. Earth's atmosphere acts like a blanket, distributing heat from day to night, from equator to poles, keeping things relatively stable. But Mercury's atmosphere is so thin it's barely there at all. Just a wispy exosphere of atoms blasted off the surface by the solar wind and micrometeorite impacts. There's nothing to hold the heat, nothing to moderate the temperature. So when the sun sets on Mercury, the heat just radiates away into space, quickly and completely. It makes you appreciate Earth's atmosphere, doesn't it? That invisible envelope of air that keeps us comfortable, that evens out the temperature extremes, that makes our world habitable. Without it, we'd be like Mercury, baking in the day, freezing at night, with nothing in between. Mars has the tallest volcano in the solar system. Olympus Mons stands 21 kilometers high, nearly 3 times the height of Mount Everest. If you stood at its base and looked up, the summit would be beyond the horizon, hidden by the curvature of Mars itself. And its base? It's roughly the size of the entire state of Arizona. It's not so much a mountain as a geological monument to the power of volcanic forces operating over billions of years. Olympus Mons is what's called a shield volcano, formed by countless eruptions of very fluid lava that flows easily and spreads out in thin layers. It's the same type of volcano as Mauna Loa in Hawaii, but on a scale that dwarfs anything on Earth. And it grew so large, partly because Mars lacks plate tectonics. On Earth, the tectonic plates are constantly moving, so a volcano might form and then drift away from its magma source. But on Mars, the crust stays put, allowing a single volcanic hotspot to build up layer after layer after layer for millions or even billions of years. The volcano is probably extinct now. Scientists haven't detected any recent activity, but recent, in geological terms, could mean millions of years. Mars is a quieter world now, its internal heat slowly dissipating, its volcanic days likely behind it. Olympus Mons stands as a monument to a more active past, when Mars was younger and more geologically alive. Imagine standing at the summit. The atmosphere up there would be so thin you'd essentially be in space. You could see the curvature of Mars stretching away in all directions, the rusty plains far below and above you, the black of space and the distant, shrunken sun. It would be a vantage point unlike anywhere else in the solar system, a mountaintop that touches the edge of space itself. Beneath the cracked, icy surface of Europa, one of Jupiter's moons, there's an ocean. Not a small one either. This hidden ocean contains more water than all of Earth's oceans combined. It's locked away beneath perhaps 15 to 25 kilometers of ice, shielded from the vacuum of space, kept liquid by tidal heating from Jupiter's immense gravitational pull. The surface of Europa is one of the smoothest in the solar system, suggesting the ice is relatively young, constantly being renewed and resurfaced. But it's also covered in cracks and ridges, long lines etched into the ice like the veins on the back of a hand. These cracks hint at the dynamic ocean below, tidal forces flexing and fracturing the ice shell, perhaps even allowing water to occasionally reach the surface before freezing again. And here's where it gets truly interesting. This ocean might not just be water. Scientists believe it could contain the chemical ingredients necessary for life. Energy from tidal heating, organic compounds delivered by meteorites, minerals from the rocky core below. All the pieces that life as we know it requires. It's one of the most promising places in the solar system to search for extraterrestrial life, a world that might harbor something living in its dark, hidden depths. We haven't sent a submarine to explore it yet, haven't even drilled through the ice, but future missions are being planned, missions that might one day splash down into that alien ocean and discover what wonders hide beneath Europa's frozen surface. Until then, we can only imagine what might be there, swimming in the dark, adapted to conditions utterly unlike anywhere on Earth, thriving in a hidden sea that's been cut off from sunlight for billions of years. The sun accounts for 99.86% of all the mass in our solar system. Let that number sink in. Everything else, all 8 planets, all their moons, all the asteroids and comets and dust and gas, every single thing that isn't the sun, makes up just 0.14% of the total. We live in what's essentially a solar monarchy, where the sun is so overwhelmingly dominant that everything else is just rounding error. Jupiter, the largest planet, contains most of that remaining 0.14%. Then comes Saturn, then the other planets in descending order. Earth, our home, our entire world with all its mountains and oceans and atmosphere. We're a tiny fraction of that already tiny fraction. Cosmically speaking, we're almost nothing in terms of mass. This lopsided distribution of matter is typical of star systems. Stars are so massive, so gravitationally dominant, that they shape everything around them. the planets exist in their orbits because the sun's gravity dictates those paths. The solar wind, that constant stream of charged particles, flows outward from the sun, filling the entire solar system with its influence. Even the farthest objects in the Oort cloud, trillions of kilometers away, are held in their distant orbits by the sun's gravitational reach. It's a humbling perspective. We think of the solar system as this collection of diverse worlds, each with its own character and features. And that's true in one sense, but in another, more fundamental sense, the solar system is the sun, and we're all just tiny bits of debris orbiting around it, warmed by its light, held by its gravity, fundamentally dependent on its presence. Without the sun, we'd be nothing, frozen, dark, adrift. Neptune is a beautiful, deep blue color, the kind of blue you might imagine if you thought of pure, perfect ocean, but darker, richer, more saturated. And the reason for this color is surprisingly mundane: methane. Neptune's atmosphere contains methane gas, which absorbs red light and reflects blue light back into space. The same gas that heats our homes and powers some of our vehicles creates, on Neptune, a world of ethereal azure beauty. But Neptune is more than just pretty. It's the most distant of the classical planets, orbiting so far from the sun that it takes 165 Earth years to complete one orbit. That means since its discovery in 1846, Neptune has only just completed its first full trip around the sun as a known world. And out there, nearly 4.5 billion kilometers from the sun, it receives 900 times less sunlight than Earth does. Yet somehow, despite this remote cold, Neptune has the strongest winds in the solar system, wind speeds reaching over 2,000 kilometers per hour, faster than the speed of sound on Earth. Where does that energy come from? Scientists aren't entirely sure. Neptune must have some internal heat source, something generating energy deep within the planet to drive those ferocious winds. Perhaps it's leftover heat from the planet's formation, slowly radiating outward. Perhaps it's something about Neptune's interior composition and structure that we don't yet understand. The planet remains mysterious in many ways. This distant blue world that we've only visited once, briefly, when Voyager 2 flew past in 1989. There's something poetic about Neptune's color, though. It's as if the universe decided that the farthest planet should be beautiful, should be worthy of contemplation, should reward our curiosity about what lies at the edge of our solar neighborhood. A blue jewel in the outer darkness, turning slowly in the cold and the silence. When the New Horizons spacecraft flew past Pluto in 2015, it revealed something nobody expected. A heart-shaped region on Pluto's surface, bright and distinct against the darker terrain surrounding it. Scientists named it Tombaugh Regio after Clyde Tombaugh, the astronomer who discovered Pluto in 1930. And this heart isn't just a pretty feature. It's a glacier made of frozen nitrogen, about the size of Texas and Oklahoma combined, slowly churning and renewing itself in ways that suggest Pluto is far more geologically active than anyone imagined. The left lobe of this heart, called Sputnik Planitia, is particularly fascinating. It's a vast plain of nitrogen ice, and it appears to be constantly convecting, warmer ice rising from below, cooler ice sinking down, creating a slow, churning motion, like a lava lamp, but on a planetary scale and over time scales of hundreds of thousands of years. The surface is divided into irregular cells, each one perhaps 10 to 20 kilometers across. where this convection creates polygonal patterns that give the region a distinctive, almost organic appearance. Nitrogen is weird stuff at Pluto's temperatures. It freezes solid, but just barely. Pluto's surface is cold enough to keep it frozen, but warm enough, relatively speaking, that the ice can still flow and deform. It's a substance caught between solid and fluid, behaving in ways that are alien to our everyday experience. And this glacier, this frozen heart, is made of it, slowly cycling, slowly moving, driven by heat from Pluto's interior and the faint warmth of the distant sun. There's something touching about Pluto having a heart, this tiny world, demoted from planet status, orbiting so far out in the cold and the dark, carrying this bright, distinctive feature that looks for all the world like a valentine to the cosmos. It reminds us that even the most distant, seemingly dead worlds can surprise us with their beauty and complexity. When you hear asteroid belt, you might picture a dense field of rocks, a navigational hazard where spacecraft have to dodge and weave to avoid collision. Science fiction has certainly given us that image. Scenes of starships threading through tumbling asteroids, narrow escapes, dramatic near misses. But the reality is far different, and in some ways, far stranger. The asteroid belt contains millions of rocks, yes, but they're so spread out, so separated by vast distances, that the belt is mostly empty space. If you were standing on one asteroid in the belt, you'd need a telescope to see the next nearest one. The average distance between asteroids is hundreds of thousands of kilometers, more than the distance from Earth to the Moon. Spacecraft routinely pass through the asteroid belt without any special maneuvering, without any concern about impacts. The belt isn't a crowded highway. It's more like a nearly empty parking lot the size of a continent, with just a few cars scattered here and there. This speaks to a fundamental truth about space. It's big, really big. Even regions we think of as crowded or dense are, by any earthly standard, almost perfectly empty. The asteroid belt, despite containing millions of objects, has a total mass that's less than our moon. If you could somehow gather up all those asteroids and squeeze them together, you'd end up with something smaller than any of the major planets. It's a humbling reminder that our intuitions about space, formed by living on a world where matter is everywhere and emptiness is rare, don't translate well to the cosmic scale. Out there, emptiness is the default, and matter is the exception. Even in regions we've named for their density, the vast majority of space is just that, space. Right now, as you lie there listening, Earth's magnetic field extends tens of thousands of kilometers into space above you, creating an invisible protective bubble called the magnetosphere. It reaches up to 65,000 kilometers on the sunward side, about 5 times Earth's radius, and stretches even farther on the night side, creating a long magnetic tail that extends for millions of kilometers downstream from the sun. This magnetic field is generated deep within Earth's core, where molten iron churns and flows, creating electric currents that generate magnetic fields in a process called the geodynamo. It's a planet-scale electric generator, running continuously, powered by the heat left over from Earth's formation and the decay of radioactive elements in the core. And it's been running for billions of years, protecting life on the surface from the constant barrage of charged particles streaming from the sun. Without this shield, the solar wind would gradually strip away Earth's atmosphere, the way it stripped away most of Mars's atmosphere billions of years ago. Cosmic rays would bombard the surface, making life as we know it nearly impossible. The magnetosphere deflects these particles, channeling them around Earth, creating those beautiful auroras, the northern and southern lights, where some particles spiral down along magnetic field lines and collide with atmosphere near the poles. You can't see the magnetosphere, can't feel it, but it's there, always there, quietly doing the work of making Earth habitable. It's one of those invisible wonders that we rarely think about, but that's absolutely essential to our existence. A magnetic embrace, holding our atmosphere close, keeping the solar wind at bay, allowing life to flourish beneath its protection. The moon is leaving us, slowly, imperceptibly, but steadily. The moon is drifting away from Earth at about 3.8 centimeters per year. That's roughly the rate at which your fingernails grow. It doesn't sound like much, and in any human lifetime, it isn't. But over geological time, it adds up. The moon is measurably farther away now than it was when dinosaurs walked the Earth. This happens because of tidal forces. The moon's gravity creates bulges in Earth's oceans, the tides. And as Earth rotates beneath these bulges, friction converts some of Earth's rotational energy into heat. That energy has to go somewhere, and where it goes is into the moon's orbit, gradually pushing it farther away. At the same time, Earth's rotation is slowing down. Days are getting longer very gradually, at a rate of about 1.7 milliseconds per century. In the age of dinosaurs, 70 million years ago, the moon appeared larger in the sky. It was about 2,500 kilometers closer than it is now. Days were shorter too, lasting only about 23.5 hours instead of 24. If you could travel back in time, you'd see a moon that loomed slightly larger overhead, and you'd experience ever so slightly shorter days and nights. And this process will continue, billions of years from now, assuming the sun hasn't expanded into a red giant and consumed everything. The moon will be so distant that it will appear much smaller than it does now. Total solar eclipses, those spectacular alignments where the moon perfectly covers the sun's disk, will no longer be possible. The moon will be too far, too small, to block the sun completely. We live in a privileged era, cosmically speaking, when the moon happens to be at just the right distance to create those perfect eclipses. Jupiter's moon Io is the most volcanically active body in the solar system. It has over 400 active volcanoes, constantly erupting, constantly resurfacing the moon with fresh lava. If you could watch Io for a few days, you'd see plumes of sulfur and sulfur dioxide shooting hundreds of kilometers into space, lava flows spreading across its surface, and the landscape itself changing in real time. The reason for all this activity is gravitational torture. Io orbits very close to Jupiter, and it's also in orbital resonance with two other large moons, Europa and Ganymede. These gravitational interactions pull and push on Io, squeezing and stretching it like a stress ball, generating enormous amounts of heat through tidal friction. It's as if Io is constantly being kneaded by invisible cosmic hands, and all that friction keeps its interior molten and active. The result is a world that looks like nothing else in the solar system. Io's surface is painted in yellows, oranges, reds, and blacks, the colors of sulfur in various forms, mixed with silicate rock. There are massive calderas, lava lakes, and volcanic mountains. The atmosphere, such as it is, consists mostly of sulfur dioxide, that gets blasted into space by volcanic eruptions and then falls back down as frost. It's a harsh, hellish place, utterly inhospitable to life as we know it. Yet there's something almost beautiful about Io's fury. It's a moon that refuses to be quiet, that's constantly active and changing, driven by forces beyond its control, but responding with volcanic vigor. In a solar system where most worlds are geologically dead or dying, Io is vibrantly, violently alive. It reminds us that planetary geology isn't always slow and subtle. Sometimes it's explosive, dramatic, and impossible to ignore. The sun's core is dense beyond everyday comprehension. If you could somehow extract a piece of the core the size of a pinhead, say about 2 millimeters across, it would weigh several tons. Not pounds, tons. You couldn't lift it. You probably couldn't even dent it with a hammer. The material is so compressed by the weight of all the sun's outer layers pressing down that atoms are squeezed together far more tightly than any material on Earth. And in this incredibly dense environment, at temperatures reaching 15 million degrees Celsius, nuclear fusion occurs. Hydrogen nuclei, protons, are moving so fast and the pressure is so intense that they can overcome their natural electromagnetic repulsion and fuse together, creating helium and releasing tremendous amounts of energy in the process. This is the source of the sun's light and heat, the power source that drives everything in our solar system. Every second, the sun converts about 600 million tons of hydrogen into helium. That sounds like an enormous amount, and it is, but the sun is so massive that it can sustain this rate for billions of years. It's been fusing hydrogen for about 4.6 billion years already, and it has enough fuel to continue for another 5 billion years or so. What's remarkable is that this fusion only happens in the core, in the innermost 25% of the sun's radius. That's where conditions are extreme enough. Outside the core, the sun's material is still incredibly hot and dense by any normal standard, but not hot and dense enough for fusion. So the energy is generated in this compact region at the center, and then it slowly works its way outward, taking hundreds of thousands of years to reach the surface before finally radiating into space as the light that warms our world. Titan, Saturn's largest moon, is one of the most extraordinary places in the solar system. It's the only moon with a thick atmosphere, thicker than Earth's in fact, and it's the only other world besides Earth where we've confirmed stable liquid on the surface. But these aren't lakes of water. They're lakes and rivers and seas of liquid methane and ethane, hydrocarbons that exist as gases on Earth, but as liquids on Titan's frigid surface, where temperatures hover around 180 degrees Celsius. The Cassini mission revealed this alien hydrological cycle in stunning detail. Methane evaporates from the lakes, rises into the atmosphere, forms clouds, and then falls as rain. The rain carves channels in Titan's icy surface, creating river networks that flow into lakes and seas. It's eerily familiar, a water cycle, but not with water. An Earth-like landscape, but profoundly alien. The largest of Titan's seas, Kraken Mare, is bigger than the Caspian Sea on Earth. It's hundreds of meters deep in places, filled with liquid hydrocarbons, with waves lapping at shores made of water ice as hard as rock. Imagine standing on that shore. The sky would be orange from the thick, hazy atmosphere. The liquid in the sea would be clear like gasoline, and overhead you'd see Saturn, enormous and ringed, hanging in the sky. Could life exist in Titan's lakes, not life as we know it. Anything based on water and carbon chemistry would freeze solid instantly. But some scientists speculate about exotic forms of life that might use liquid methane as a solvent instead of water, that might be based on different chemistry entirely. It's speculative, perhaps unlikely, but the mere possibility that such radically different life could exist reminds us that biology might be more diverse and adaptable than we imagine. The sun is made almost entirely of just two elements, hydrogen and helium. About 73% of its mass is hydrogen. About 25% is helium, and everything else, all the other elements in the periodic table, from lithium to uranium, makes up just 2%. All the carbon, oxygen, nitrogen, iron, silicon, all the elements that seem important to us because they make up our world and our bodies, they're trace contaminants in the sun, barely worth mentioning. This composition isn't unique to the sun. It's typical of stars, and indeed of the universe as a whole. Hydrogen and helium are the two lightest elements, and they're by far the most abundant because they were created in the Big Bang itself. Everything else, all the heavier elements, had to be forged later, in the cores of stars or in supernova explosions. This means that the atoms in your body, the carbon in your DNA, the calcium in your bones, the iron in your blood, all of those atoms are cosmically rare. They're products of stellar nucleosynthesis, created when ancient stars fused lighter elements into heavier ones, and then scattered into space when those stars died. You are, quite literally, made of stardust, and not just in a poetic sense. The atoms that comprise you were forged in the hearts of stars that lived and died billions of years before the sun even existed. The sun, by contrast, is made mostly of the primordial stuff of the universe, the hydrogen that's been around since the beginning. It's converting some of that hydrogen into helium through fusion, gradually enriching itself with heavier elements. But this process is slow. Most of the sun's material has remained unchanged since it formed 4.6 billion years ago, a sample of what the early solar system was made of, a connection to the universe's distant past. Venus is covered in volcanoes. Over 1,600 major volcanoes have been identified, and there are likely countless smaller ones. It's the most volcanic planet in our solar system in terms of sheer numbers, and its surface shows clear signs of relatively recent volcanic activity. Though recent, in geological terms, could mean anywhere from a few million to a few 100 million years ago. The reason for all these volcanoes is still debated. Venus doesn't have plate tectonics like Earth does, where volcanic activity is concentrated at plate boundaries. Instead, Venus's volcanism seems to be distributed more randomly, perhaps driven by plumes of hot material rising from the mantle. Some scientists think Venus might have experienced catastrophic resurfacing events in its past, where large portions of the surface melted and reformed over relatively short periods. Geologically speaking, the surface of Venus is hostile in every conceivable way. The atmospheric pressure is 90 times that of Earth's, equivalent to being a kilometer underwater. The temperature is hot enough to melt lead. The atmosphere is mostly carbon dioxide with clouds of sulfuric acid, and yet beneath all this hellishness, Venus is Earth's sister planet, nearly the same size, nearly the same mass, formed from the same materials in the same region of the solar nebula. What went wrong on Venus? Why did it become a hell world while Earth became a paradise? The answer probably involves a runaway greenhouse effect. Venus's thick atmosphere trapped heat, which evaporated any oceans it might have had, which released more greenhouse gases, which trapped more heat, in a vicious cycle that ended with the hostile world we see today. It's a cautionary tale about atmospheric composition and climate feedback loops, relevant to our own planet as we grapple with our own greenhouse gas emissions. Here's something that seems impossible but is mathematically true. The space between Earth and the Moon is large enough that you could fit all the other planets in the solar system: Jupiter, Saturn, Uranus, Neptune, Mars, Venus, and Mercury in a line between them, and still have a bit of room left over. The Moon orbits at an average distance of 384,400 kilometers from Earth. Meanwhile, if you add up the diameters of all the other planets, you get approximately 380,000 kilometers. It's close, but it fits. Jupiter alone accounts for most of that distance with its 140,000 kilometer diameter. But even with all the planets lined up, you'd still have a few thousand kilometers of clearance. This fact always catches people by surprise because the Moon seems relatively close. We can see it clearly with the naked eye. Spacecraft can reach it in just a few days. But space is deceptive that way. Distances that seem manageable turn out to be enormous, and voids that seem empty contain vast amounts of room. It also illustrates something about the scale of the solar system. If Earth and Moon were really that close together compared to the sizes of the planets, then the solar system as a whole must be incomprehensibly large. Jupiter orbits roughly 2,000 times farther from the Sun than the Moon is from Earth. Neptune is 30 times farther from the Sun than Earth is. The distances involved are so large that our everyday intuitions completely fail. We can state the numbers, we can do the math, but truly grasping those scales? That's harder. Perhaps it's enough to know that space is big, really big, far bigger than our earthbound minds can easily comprehend. Stars don't actually twinkle. This is one of those facts that feels wrong because we've all seen stars twinkling in the night sky. They shimmer and dance, their light seeming to pulse and flicker. But that twinkling isn't coming from the stars themselves. It's coming from Earth's atmosphere, from the layers of air between us and those distant points of light. As starlight passes through our atmosphere, it encounters pockets of air with different temperatures and densities: warm air, cool air, turbulent currents, all creating subtle variations in how light bends as it travels. These variations cause the star's position to shift ever so slightly, back and forth, dozens of times per second. Our eyes perceive this as twinkling, the star appearing to change in brightness and position, dancing in the sky. Astronauts in space see something different. Above the atmosphere, stars shine with steady, unwavering light. They're described as looking like brilliant jewels against the black velvet of space, constant and pure. No twinkling, no shimmering, just clean, steady points of light. It's one of the many subtle ways that space is different from what we experience on Earth's surface. Planets, interestingly, twinkle less than stars, because planets are closer and appear as tiny disks rather than points of light. Even though we can't resolve those disks with our naked eyes, the atmospheric effects average out. Multiple points on the planet's disk are being affected differently, and the overall effect is more stable. So if you see a bright object in the sky that isn't twinkling much, there's a good chance it's a planet, Venus, Jupiter, Mars, or Saturn, rather than a star. It's a small thing, this twinkling, but it reminds us that we're looking at the universe through a veil, that our atmosphere, as essential as it is to life, also distorts and alters what we see. The universe in its pure, unfiltered state is something we can only glimpse from above that veil, or through instruments that compensate for atmospheric distortion. The nearest star to our Sun is called Proxima Centauri, and it's 4.24 light-years away. That means the light we see from it left that star 4.24 years ago. If you look at Proxima Centauri tonight, you're seeing it as it was when current events from 4 years ago were happening on Earth. But light travels fast, absurdly fast, at 300,000 kilometers per second. The real mind-bending part comes when you think about how long it would take us to actually get there. Our fastest spacecraft, Voyager 1, is currently traveling at about 17 kilometers per second relative to the Sun. At that speed, it would take roughly 80,000 years to reach Proxima Centauri. 80,000 years. That's longer than all of recorded human history. That's long enough for human civilization to rise, fall, and rise again multiple times. And that's to reach our nearest neighbor, the closest star to our own. Proxima Centauri is a red dwarf, much smaller and cooler than our Sun. It's actually part of a triple star system. It orbits the binary pair Alpha Centauri A and B at a vast distance, taking over 500,000 years to complete one orbit. And remarkably, Proxima Centauri has at least one planet, Proxima Centauri b, discovered in 2016. This planet orbits in what might be the star's habitable zone, though whether it's actually habitable is highly uncertain, given the star's tendency to emit powerful flares. Still, the thought that our nearest stellar neighbor has planets, that there might be worlds orbiting the very closest stars to our own, ignites the imagination. If we ever do become an interstellar species, Proxima Centauri will likely be our first destination. But with current technology, that journey remains firmly in the realm of science fiction, a reminder that the universe, for all our technological progress, remains stubbornly vast. Imagine taking a teaspoon, a normal kitchen teaspoon, the kind you'd use to stir your tea, and filling it with neutron star material. That teaspoon would weigh about 6 billion tons, not 6 billion pounds, 6 billion tons. It would weigh as much as about 900 Great Pyramids of Giza, all compressed into a volume you could hold in your hand, if your hand could somehow support such impossible weight. Neutron stars are what remain after massive stars explode in supernovae. The core collapses so completely, so catastrophically, that protons and electrons are crushed together into neutrons. The resulting object is incredibly dense, a neutron star with the mass of about 1.4 to 2 times the Sun's mass gets compressed into a sphere only about 20 kilometers across. Its matter compressed to the absolute limit, just shy of collapsing into a black hole. At these densities, matter behaves in ways that are almost impossible to comprehend. The neutrons are packed so tightly together that they essentially touch. There's no empty space between them. Some theoretical models suggest that deep in the core, matter might exist in even more exotic forms, quark matter, where the neutrons themselves break down into their constituent quarks. But we're honestly not sure. Neutron stars represent conditions we can't replicate in any laboratory, pressures and densities beyond anything we can directly study. If you could somehow stand on a neutron star's surface, which you couldn't for numerous reasons, Gravity would be so intense that you'd be flattened into a layer of atoms less than a millimeter thick. Mountains on neutron stars are measured in millimeters because gravity smooths everything down. The escape velocity is about half the speed of light. They're objects that exist at the extreme edge of what physics allows, right up against the boundary where matter gives up and collapses into a black hole. Some neutron stars spin hundreds of times per second. These are called pulsars, and they're among the most precise natural clocks in the universe. As they spin, they emit beams of radiation from their magnetic poles, and if those beams happen to sweep across Earth, we detect regular pulses, like a lighthouse beam sweeping past a distant ship. The fastest known pulsar rotates 716 times per second. That's hard to even visualize. An object the size of a city with more mass than the sun, spinning so fast that its surface is moving at about 15% of the speed of light. The forces involved are staggering. Only the intense gravity holding the neutron star together prevents it from flying apart, and these pulsars are remarkably stable. Their rotation rate is so regular that millisecond pulsars can rival atomic clocks in their precision. Astronomers use them to test fundamental physics. Einstein's general relativity, for instance, makes specific predictions about how pulsars should behave, and observations confirm these predictions with extraordinary accuracy. Pulsars have also been used to search for gravitational waves, subtle ripples in space-time that cause tiny variations in the pulsar's apparent pulse arrival times. The idea that these objects, the crushed remnants of dead stars, exotic objects that shouldn't even exist by everyday logic, end up serving as some of the universe's most precise timekeepers, has a certain poetic irony to it. They're monuments to stellar death, but also tools for exploring the fundamental nature of space, time, and gravity. Nature takes the aftermath of catastrophe and somehow creates precision and order. Every single second, the sun converts about 4 million tons of matter into pure energy. Think about that. 4 million tons. Gone. Transformed into light and heat through Einstein's famous equation, E = mc2. The c in that equation is the speed of light, and it's squared, which means that even a tiny amount of mass represents an enormous amount of energy. This is nuclear fusion in action, hydrogen nuclei fusing into helium, and in the process, losing a tiny bit of mass that gets converted into energy. The mass loss per fusion reaction is small, but the sun is fusing hydrogen at such a tremendous rate that those small losses add up to 4 million tons every second. And yet, and this is the truly remarkable part, the sun has been doing this for 4.6 billion years, and it can continue for another 5 billion years or so. Despite losing 4 million tons per second, the sun has enough fuel to sustain this for billions of years. That speaks to how massive the sun is, how much hydrogen it contains. It's converting 0.06% of its mass into energy per second, a rate that seems almost negligible, but sustained over billions of years. It's enough to power an entire solar system. Life on Earth, everything we see and touch and experience, is powered by this conversion. The warmth of sunlight, the energy in the food we eat, the wind and rain and ocean currents, all of it traces back to nuclear fusion in the sun's core, to hydrogen atoms being crushed together under unimaginable pressure and heat, releasing energy that eventually makes its way to the surface and then out into space, where a tiny fraction of it happens to fall on Earth and make everything possible. Red dwarf stars, the most common type of star in the universe, can live for trillions of years, not billions, trillions. To put that in perspective, the universe itself is only 13.8 billion years old. That means every red dwarf that has ever formed is still shining today. Not one has died yet. Not one has exhausted its fuel and faded away. They've barely started their lives. Red dwarfs are small stars, typically between 8% and 50% of the sun's mass. They burn their fuel incredibly slowly because they're not very hot. Their cores reach temperatures just barely high enough to sustain hydrogen fusion. This means they're dim, far dimmer than the sun, but also incredibly long-lived. A red dwarf with 10% of the sun's mass might live for 10 trillion years. What will the universe look like in 10 trillion years? We can only speculate. All the larger stars will be long dead. Galaxies will have evolved, merged, perhaps dispersed. The cosmic microwave background will have cooled further, faded to near invisibility. But red dwarfs will still be there, patiently fusing hydrogen, casting their dim red light into the darkness, outlasting nearly everything else. There's something comforting about that, isn't there? In a universe where most things are temporary, where stars die and galaxies collide and everything seems to be in constant flux, red dwarfs are the steady, reliable constants. They're the tortoises in a cosmic race full of hares, slow, unassuming, easy to overlook, but ultimately the ones that endure longest. When you look at Betelgeuse, that distinctive red star in the constellation Orion, marking the hunter's shoulder, you're seeing light that left the star about 650 years ago. That light began its journey when the Ming Dynasty ruled China, when the Black Death was still a recent memory in Europe, when the Renaissance was just beginning. And it's been traveling through space ever since, crossing the vast empty distances between the stars, until finally it entered our atmosphere and reached your eye. This means that if Betelgeuse exploded today, and it might, it's a red supergiant near the end of its life, the kind of star that ends in a spectacular supernova, we wouldn't know about it for roughly 650 years. The star could already be gone, replaced by an expanding cloud of gas and a neutron star or black hole, and we'd still see it twinkling up there in Orion, completely unaware that we're looking at something that no longer exists. This time delay is a fundamental feature of the universe. Light travels at a finite speed, so we always see distant objects as they were in the past, never as they are right now. The sun? We see it as it was 8 minutes ago. Alpha Centauri? 4.24 years ago. The Andromeda Galaxy? 2.5 million years ago. The most distant objects we can see with our telescopes existed billions of years ago, when the universe was young. In a sense, astronomy is the only field of science where we directly observe the past. We're not reconstructing it from evidence or making inferences. We're literally looking at it, receiving light that has traveled across space and time to tell us about distant places and distant eras. Every photon that enters your eye from a star is a messenger from the past, carrying information about when it was emitted, what it passed through on its journey, and the nature of its source. The sun's light takes about 8 minutes and 20 seconds to reach Earth. This means that when you look at the sun, though you shouldn't look directly at it, it can damage your eyes. You're seeing it as it was just over 8 minutes ago. Not as it is now, but as it was in the recent past. The sun could theoretically vanish right now, and we wouldn't know for 8 minutes and 20 seconds. The sky would stay bright, the world would stay warm, and then suddenly, without warning, it would all end. Of course, the sun isn't going to vanish. Stars don't work that way. But the principle stands: there's no such thing as instantaneous information at cosmic scales. Everything we know about the sun is old news, delayed by the time it takes light to cross the 150 million kilometers between the sun and Earth. This creates interesting effects: solar flares and coronal mass ejections, eruptions on the sun's surface that send radiation and charged particles streaming into space, affect Earth about 8 minutes later for the light and electromagnetic radiation, but 1 to 3 days later for the particles themselves, which travel much slower. This gives us a warning system of sorts. We can see a flare happen and then prepare for the particle storm that will arrive in a day or two, potentially disrupting satellites, power grids, and communications. There's something philosophically interesting about this delay, too. It means the now that we experience on Earth is different from the now happening on the Sun, or on Mars, or anywhere else in the universe. Simultaneity, the idea that events happen at the same time, becomes slippery at cosmic scales. Einstein's relativity tells us that there's no universal now, no absolute time that ticks the same everywhere. Time is local, personal, dependent on your motion and position in a gravitational field. The 8-minute delay to the sun is just one small example of this deeper truth. Most stars don't live alone. Binary star systems, where 2 stars orbit each other, are actually more common than solitary stars like our sun. Some estimates suggest that 85% or more of star systems contain multiple stars. We're the exception, not the rule. Our single sun, our orderly system of planets orbiting in more or less the same plane, is a relatively unusual configuration. Imagine what it would be like to live on a planet in a binary system. Depending on the orbital configuration, you might have 2 sunrises and 2 sunsets each day. Or perhaps one sun would always be in the sky while the other rose and set. The shadows would be complex, sometimes doubled, sometimes converging. Nighttime might never truly be dark if one sun set before the other rose. The rhythms of day and night that we take for granted would be completely different. Some binary systems have very close orbits, with the stars so near each other that they exchange material, pulling gas from one star to the other. These can create spectacular phenomena: novae, where stolen material piles up on a white dwarf and periodically ignites in a thermonuclear explosion, brightening the system dramatically. Other binaries are widely separated, orbiting each other at distances measured in thousands of astronomical units, barely influencing each other at all. And then there are triple star systems, quadruple systems, even systems with 6 or more stars all bound together in complex orbital dances. The dynamics of these systems can be chaotic. Predicting the motions of 3 or more bodies mutually attracting each other gravitationally is one of the classic problems in physics, one that generally doesn't have neat, closed-form solutions. Yet nature creates these systems routinely, and they persist for millions or billions of years, their complex dances somehow remaining stable despite the chaotic mathematics underlying them. A star's color reveals its temperature, and the relationship is counterintuitive if you're used to thinking about fire on Earth. Blue stars are the hottest, with surface temperatures above 30,000 Kelvin, White stars are cooler, around 10,000 Kelvin. Yellow stars like our Sun are cooler still, at about 5 to 800 Kelvin. Orange stars are around 4,000 Kelvin. And red stars, the coolest of all, can be as low as 2,500 Kelvin. Still hot enough to vaporize any known material, but cool by stellar standards. This color-temperature relationship comes from blackbody radiation, the way hot objects emit light. As something gets hotter, it emits more light, and the peak wavelength shifts toward the blue end of the spectrum. Cool red embers in a fire are actually cooler than white-hot metal, which is cooler than a blue flame. Stars follow the same principle, just at much higher temperatures. Our Sun appears yellow-white to us, placing it comfortably in the middle of the temperature range. It's sometimes called a yellow dwarf, though that's a bit of a misnomer. The Sun is actually white when viewed from space. Our atmosphere scatters the blue light, making the Sun appear more yellow from the surface. But regardless, the Sun is neither the hottest nor the coolest type of star. It's average in almost every way: mass, temperature, luminosity. It's the cosmic equivalent of a middle-aged, middle-class citizen, unremarkable in the stellar census, but perfectly suited to supporting life on the planet that orbits it. Those blue stars, the hot ones, they burn through their fuel quickly, living only millions of years before exhausting themselves in supernovae. Red stars, the cool ones, sip their fuel slowly and live for trillions of years. There's a trade-off between brightness and longevity, between burning hot and burning long. The universe offers many strategies for being a star, and each color in the rainbow represents a different way of existing, a different balance between temperature, mass, lifespan, and luminosity. Magnetars are neutron stars with magnetic fields so powerful they defy comprehension. We're talking about magnetic fields 1 trillion times stronger than Earth's. To put that in perspective, a magnetar halfway to the moon, about 200,000 kilometers away, could strip the information from every credit card on Earth. From that distance, its magnetic field would be strong enough to affect every magnetic stripe, every hard drive, every compass, rendering them all useless in an instant. But it gets stranger. Within about 1,000 kilometers of a magnetar's surface, the magnetic field becomes so intense that it starts to affect the fundamental properties of matter. Atoms become elongated, stretched into cigar shapes by the field. The vacuum itself behaves oddly, becoming birefringent, meaning light traveling in different directions moves at slightly different speeds. Physics as we normally understand it starts to break down. Magnetars occasionally have starquakes, sudden shifts in their crusts that release enormous amounts of energy. These events can produce bursts of gamma rays and X-rays so powerful that they're detectable across the galaxy. In 2004, a magnetar about 50,000 light-years away had a starquake that affected Earth's upper atmosphere, ionizing it temporarily. An event that far away, and it still reached across the galaxy to touch our world. There aren't many magnetars known. Only a few dozen have been identified. They're rare objects, and we're still trying to understand exactly how they form and why their magnetic fields are so extreme. But they represent physics at its most extreme. Matter and energy pushed to absolute limits, creating conditions that we can barely model mathematically, and certainly can't reproduce in any laboratory. Sirius, the brightest star visible from Earth, has been known since ancient times. It's so bright partly because it's relatively close, only about 8.6 light years away, and partly because it's genuinely luminous, about 25 times more luminous than our sun. Ancient Egyptians based their calendar on its heliacal rising, the day when Sirius became visible just before dawn, after a period of being hidden by the sun's glare. They called it Sopdet, associated it with the goddess Isis, and knew that its appearance heralded the annual Nile flood. But Sirius has a secret. It's actually a binary system. Orbiting the bright star we see, Sirius A, is a much smaller, dimmer companion called Sirius B. This companion is a white dwarf, the collapsed core of a star that exhausted its fuel long ago. White dwarfs are incredibly dense. Sirius B has about 98% of the sun's mass compressed into an object roughly the size of Earth. That teaspoon of white dwarf material we discussed earlier, it would weigh several tons. Sirius B wasn't discovered until 1862, when telescope maker Alvin Clark was testing a new lens and noticed a faint point of light near Sirius. This made sense of something astronomers had noticed for years. Sirius A's position wobbled slightly, as if something invisible were tugging on it. That invisible something turned out to be Sirius B, pulling on its brighter companion through their mutual gravitational attraction. The two stars orbit each other once every 50 years. Their dance slowly unfolding across the sky. Sometimes they're relatively close together, sometimes farther apart, but always linked, always influencing each other. It's a reminder that even the stars we think we know, the ones that have been familiar to humans for millennia, can still hold surprises, still have hidden companions waiting to be discovered when we look closely enough. Stars are born in giant clouds of gas and dust called nebulae. These clouds are vast, often hundreds of light years across, containing enough material to create thousands or even millions of stars. They're cold, just a few degrees above absolute zero, and incredibly diffuse. In most places, they're better vacuums than anything we can create in laboratories on Earth. Yet somehow, over millions of years, gravity slowly pulls this material together. The Orion Nebula is one of the closest stellar nurseries to Earth, about 1,350 light years away. On a dark night, you can see it with the naked eye as a fuzzy patch in the sword of Orion. But through a telescope, it reveals itself as a spectacular cloud of glowing gas, illuminated by young, hot stars that have recently formed within it. These stars are still in their infancy, cosmically speaking. Many are less than 1 million years old, babies compared to our 4.6 billion-year-old sun. Within the Orion Nebula, astronomers have found protostars, stars that are still forming, still gathering material, not yet hot enough in their cores to sustain fusion. Around many of these protostars are protoplanetary disks, flattened clouds of gas and dust that might someday become planets. We're watching the birth process of solar systems, seeing in these distant clouds what our own solar system must have looked like 4.6 billion years ago. The process is violent and chaotic. Young stars emit powerful stellar winds that blow away nearby gas. They flare and fluctuate unpredictably. Sometimes multiple protostars form close together and gravitationally interact, ejecting one or more of them from the system. It's not a gentle process, this stellar birth, but a turbulent emergence from darkness into light, from cold, diffuse clouds into hot, dense spheres where nuclear fusion ignites and a star begins its long life. When massive stars die, they don't fade quietly. They explode in events called supernovae, blasts so powerful they can briefly outshine entire galaxies. For a few weeks, a single dying star can emit as much light as 100 billion stars combined. These explosions are visible across cosmic distances. Astronomers regularly detect supernovae in galaxies hundreds of millions of light years away. But supernovae aren't just spectacular light shows. They're essential to the universe's chemistry, the cosmic forges where heavy elements are created. During a star's normal life, fusion in the core creates elements up to iron. But elements heavier than iron, gold, platinum, uranium, require more energy to create than fusion releases. They can only be made in extreme conditions, and supernovae provide those conditions. In the moments before a supernova explosion, the collapsing core of the star reaches temperatures of billions of degrees. In the shock wave that follows, free neutrons are captured by atomic nuclei in rapid succession, building up heavier and heavier elements. This process, called the R process, rapid neutron capture, creates roughly half of all elements heavier than iron. The other half comes from other extreme events like neutron-star collisions. So the gold in any jewelry you own, the silver in your electronics, the uranium in nuclear reactors, all of it was forged in supernovae or similar cataclysmic events. These atoms were created in stellar death, then scattered into space, where they eventually became part of the cloud that formed our solar system. You're living with the debris of ancient stellar explosions. The universe recycles, and destruction gives rise to new creation. White dwarfs are the endpoints of stellar evolution for most stars, including our Sun. They're no longer fusing anything. They've exhausted all their fuel. They shine only because they're still hot, gradually radiating away their thermal energy into space. Over time, they cool down, fading from white to yellow to red to brown, eventually becoming cold, dark objects called black dwarfs. But here's the thing, the universe isn't old enough for any black dwarfs to exist yet. White dwarfs cool incredibly slowly. The coolest, oldest white dwarfs we've found are still around 3,000 or 4,000 Kelvin, still glowing with a dull red light. To cool all the way to the background temperature of the universe, to become truly black, would take trillions of years. The universe is only 13.8 billion years old. Black dwarfs are purely theoretical, objects that will exist in the far future but don't exist now. Imagine that future universe, trillions of years from now. Star formation will have mostly ceased. All the available gas will have been incorporated into stars or locked up in stellar remnants. The remaining red dwarfs will still be shining, but most other stars will be gone, replaced by white dwarfs, neutron stars, and black holes. And the oldest white dwarfs will finally have cooled completely, becoming black dwarfs, dark and cold, invisible except for the gravitational effects they exert on anything nearby. It's a melancholy vision, perhaps, this far future where most of the light has gone out. But it's also peaceful in its way, the universe settling into a long, quiet twilight, the frenetic activity of the stellar era giving way to darkness and stillness. Black dwarfs will be the tombstones of stars, enduring monuments to the cosmic past when fusion still lit the universe, when there was still free energy to burn. Right now, as you listen to this, the sun is emitting a constant stream of charged particles, mostly electrons and protons, that flows outward in all directions. This is called the solar wind, and it fills the entire solar system, creating a bubble called the heliosphere that extends far beyond the orbits of the planets. The solar wind isn't trivial. It moves at speeds of 300 to 800 kilometers per second, and it carries magnetic fields with it, creating a complex, turbulent environment. Near Earth, the solar wind has a density of only about 5 particles per cubic centimeter, far more tenuous than even the best laboratory vacuums. But at those speeds and across such vast scales, it has significant effects. When the solar wind encounters Earth's magnetic field, it compresses it on the sunward side and stretches it out into a long tail on the night side. Some of the particles get funneled along magnetic field lines toward the poles, where they collide with atoms in the upper atmosphere, creating auroras, the northern and southern lights. Those shimmering curtains of green and red and purple light are the visible manifestation of the solar wind interacting with Earth's magnetic shield. The solar wind also extends beyond the planets, pushing against the interstellar medium, the very thin gas that fills the space between stars. Somewhere around 120 astronomical units from the Sun, roughly 3 times Neptune's distance, the solar wind finally weakens enough that it can't push any farther. This boundary is called the heliopause, and it marks the edge of the Sun's influence, the boundary between our solar system and interstellar space. Both Voyager spacecraft have crossed this boundary, becoming the first human-made objects to enter interstellar space, sailing beyond the reach of the solar wind into the galaxy beyond. Some stellar nurseries are truly enormous, containing enough material to birth not just hundreds, but millions of stars. The Tarantula Nebula in the Large Magellanic Cloud is one such region. It's so bright that if it were as close to us as the Orion Nebula, it would cast shadows on Earth at night. It's a star-forming region on a scale that dwarfs anything in our own galaxy. These massive nurseries often create stellar clusters, groups of stars born together, all roughly the same age, still gravitationally bound to each other. Some clusters are loose associations that will eventually disperse as the stars drift apart. Others are tightly bound globular clusters containing hundreds of thousands or even millions of stars, all packed into a relatively small volume. The stars in a cluster share a common origin. They formed from the same cloud at roughly the same time, from material with the same composition. This makes them invaluable to astronomers studying stellar evolution. By examining stars of different masses but the same age and composition, we can understand how mass affects a star's life and development. Clusters are like cosmic laboratories, natural experiments in stellar physics, and there's something poetic about the idea that stars can be born together, siblings in a sense, sharing their origin even if they eventually drift apart. Some clusters remain bound for billions of years, their member stars orbiting around the cluster's center of mass in a complex gravitational dance. Others disperse relatively quickly, the stars scattering throughout the galaxy, but retaining in their composition a memory of their shared birth, a chemical signature that links them to their siblings even after they've long since parted ways. It seems like it should be straightforward. Bigger stars have more fuel, so they should live longer. But the opposite is true. Massive stars burn through their fuel far faster than smaller stars, living only millions of years, while small red dwarfs can live for trillions. It's one of the paradoxes of stellar evolution. Having more fuel doesn't help if you burn it much faster. The reason comes down to how stars maintain equilibrium. A star is a balancing act between gravity trying to compress it and the pressure from fusion pushing outward. More massive stars have stronger gravity, which means they need higher core temperatures and pressures to balance it. Higher temperatures mean faster fusion reactions, which means they consume their fuel more quickly. A star with 20 times the Sun's mass might live only 10 million years. A star with 1.5 times the Sun's mass might live 3 billion years. Our Sun, at one solar mass, will live about 10 billion years total, and a red dwarf with 0.1 times the Sun's mass, perhaps 10 trillion years or more. The relationship is steep. Small differences in mass create enormous differences in lifespan. This has implications for life in the universe. Massive, bright stars don't live long enough for complex life to evolve on any orbiting planets. By the time intelligence might emerge, the star would already be dead. Red dwarfs live almost forever by comparison, but they're dim and prone to violent flares, which might make them poor hosts for life. Sun-like stars, medium-sized and medium-lived, might occupy a sweet spot, bright enough to support life, stable enough to last long enough for that life to evolve. We exist, perhaps, because our sun is average, neither too large nor too small, burning its fuel at just the right rate. In 1930, a young Indian astrophysicist named Subrahmanyan Chandrasekhar calculated something remarkable while sailing from India to England to begin his graduate studies. He worked out that there's a maximum mass for white dwarfs. No white dwarf can exceed about 1.4 times the Sun's mass without collapsing further. This became known as the Chandrasekhar limit, and it's one of the most important numbers in astrophysics. White dwarfs are supported by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being squeezed too close together. But Chandrasekhar realized that above a certain mass, even electron degeneracy pressure isn't enough. Gravity wins. The star collapses further, and you get a neutron star, or, if the mass is high enough, a black hole. This limit has profound implications. It helps us understand type Ia supernovae, a specific kind of supernova that occurs when a white dwarf in a binary system accumulates material from its companion and approaches the Chandrasekhar limit. At that point, it becomes unstable and explodes. Because this always happens at roughly the same mass, type Ia supernovae have roughly the same intrinsic brightness, which makes them useful as standard candles for measuring cosmic distances. Chandrasekhar was only 19 when he made this calculation. He went on to have a long, distinguished career, winning the Nobel Prize in 1983. But that initial insight, worked out in longhand on a ship crossing the Indian Ocean, established a fundamental limit on stellar structure, a boundary written into the laws of physics themselves. Above 1.4 solar masses, a white dwarf cannot exist. The universe allows no exceptions. Some stars aren't constant. They pulsate, swelling and shrinking rhythmically, changing in brightness with periods ranging from hours to months. These are called variable stars, and they've been invaluable to astronomy, helping us measure cosmic distances and understand stellar structure. The pulsation happens because these stars are unstable. They heat up, expand, cool down, contract, then heat up again in a regular cycle. Imagine the star breathing, its outer layers moving in and out by a significant fraction of its radius. As it expands, it cools and dims. As it contracts, it heats up and brightens. This creates a regular pattern of brightness changes that we can observe from Earth. One type of variable star, called Cepheid variables, has a special property. The period of pulsation is directly related to the star's intrinsic brightness. Longer period means brighter star. This relationship, discovered in the early 1900s by Henrietta Swan Leavitt, gave astronomers a powerful tool. By measuring a Cepheid's period, you can determine how bright it really is. By comparing that to how bright it appears from Earth, you can calculate its distance. Edwin Hubble used Cepheids in the 1920s to prove that some of the fuzzy nebulae visible in the sky were actually distant galaxies far beyond the Milky Way. This expanded the known universe by orders of magnitude in one stroke. Later, Cepheids helped establish Hubble's law, the relationship between a galaxy's distance and how fast it's moving away from us, which led to our understanding of cosmic expansion and ultimately to the Big Bang theory. All because some stars pulse like cosmic heartbeats, keeping time in the darkness, their rhythms revealing the universe's vast scale. Our galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. That's a range, not a precise number, because we honestly can't count them all. We can estimate based on the galaxy's mass, its brightness, statistical sampling of different regions, but an exact census. That's beyond our capabilities. Most stars in the Milky Way remain nameless, uncatalogued, unexplored. We've studied perhaps less than 1% of them in any detail. Think about that uncertainty for a moment. The difference between 100 billion and 400 billion is 300 billion stars, more stars than the total number of stars in many entire galaxies. We're uncertain by an amount that would constitute multiple large galaxies. It speaks to the difficulty of studying something from the inside, of trying to map a structure when you're embedded within it. The Milky Way is a barred spiral galaxy with a central bar-shaped structure and spiral arms sweeping out from it. Our Sun sits about 26,000 light-years from the galactic center, roughly halfway out to the edge, in what's called the Orion Arm or Orion Spur, a minor spiral arm between two major ones. From our vantage point, we see the galaxy edge on, as a band of light stretching across the sky, thicker toward the center where more stars are concentrated. Ancient cultures saw this band and created stories to explain it. The Greeks called it the Milky Way, Galaxias Kyklos, the Milky Circle, because it resembled spilled milk. The Romans had a similar interpretation. Other cultures saw it as a river, a path, a seam in the sky. All were trying to explain this luminous band, not knowing they were seeing billions of distant stars, so numerous and far away that they blur together into a continuous glow, the collective light of our cosmic home viewed from within. Right now, our solar system is moving through space at about 828,000 kilometers per hour relative to the galactic center. That's roughly 230 kilometers per second. We're orbiting the Milky Way's center, just as Earth orbits the Sun, caught in the galaxy's gravitational embrace, following a path through space that will travel for hundreds of millions of years. At this tremendous speed, it still takes us about 230 million years to complete one orbit around the galaxy. Astronomers sometimes call this period a galactic year. The last time we were at this position in our orbit, dinosaurs were just beginning to emerge on Earth. The time before that, complex life was only just starting to diversify in the oceans. In all of human history, we've traveled only about 1/1300th of one galactic orbit. and we're not alone in this motion. Everything in our neighborhood of the galaxy is moving together. Nearby stars, the planets, even the molecular clouds between the stars. We're all caught in the same gravitational current, flowing together around the galactic center like leaves floating downstream in a vast cosmic river. The path we follow isn't perfectly circular either. The galactic disk has structure, spiral arms where star density is higher, regions between arms where it's lower. As we orbit, we pass through these different regions, spending time in spiral arms and then emerging into quieter spaces. Some scientists have speculated that these passages through spiral arms might influence Earth's climate or evolution, though the evidence for this remains controversial. Either way, we're wanderers on a cosmic scale, never staying in the same neighborhood for long, our solar system drifting through the galaxy like a ship on a centuries-long voyage. The Milky Way and Andromeda galaxies are approaching each other at about 110 kilometers per second. In about 4.5 billion years, roughly the same age as Earth is now, they'll collide. Or perhaps collide isn't quite the right word. They'll merge, interpenetrating each other in a slow-motion dance that will take hundreds of millions of years to complete. When galaxies collide, individual stars rarely hit each other. The distances between stars are so vast that most stars will pass through the other galaxy without any direct impacts. But gravitational interactions will be profound. Stars will be flung into new orbits. The galactic structures will be disrupted, the neat spiral patterns giving way to chaos and then eventually settling into a new configuration, likely an elliptical galaxy. Astronomers have already given this future galaxy a name, Milkomeda, or sometimes Milkdromeda. It will be larger than either parent galaxy, containing perhaps 1 trillion stars, a giant elliptical galaxy that will dominate the local group of galaxies. What will happen to our solar system during this merger? It's hard to say precisely. We might be flung into a different orbit, perhaps farther from the galactic center, perhaps closer. We might be ejected entirely, becoming part of the intergalactic medium, a lonely solar system drifting between galaxies. Or we might continue much as we are, relatively undisturbed by the larger chaos happening around us. The probabilities of any individual star being significantly affected are actually quite low, simply because space is so empty. But 4.5 billion years is a long time. The sun will be nearing the end of its main sequence life by then, beginning to swell into a red giant. Earth's oceans will likely have boiled away. The collision with Andromeda, dramatic as it will be on cosmic scales, might be the least of Earth's concerns. Fact 44. Sagittarius A, our galactic center. At the very center of the Milky Way, hidden behind thick clouds of dust and gas, there's a supermassive black hole called Sagittarius A, pronounced Sagittarius A star. It has a mass of about 4 million times the Sun's mass, all concentrated into a region smaller than Mercury's orbit. It's the gravitational anchor of our galaxy, the object that everything else orbits around. For a supermassive black hole, Sagittarius A is surprisingly quiet. It's not currently consuming much material, so it's not producing the brilliant radiation that we see from more active galactic nuclei. It's relatively dormant, occasionally swallowing small amounts of gas or an unlucky star that wanders too close, but mostly just sitting there, its gravity shaping the orbits of stars near the galactic center. Astronomers have been tracking these stars for decades, watching them orbit the black hole, using their motions to measure Sagittarius A's mass and confirm that it's truly a black hole. Some stars orbit so close that they reach speeds of up to 5,000 kilometers per second, about 2% of the speed of light. Their orbits are so extreme, so fast, that we can actually observe them move noticeably over just a few years of observation. In 2022, astronomers released the first image of Sagittarius A, or rather, the glowing material around it, the accretion disk and the photon ring created by light bending around the black hole's immense gravity. It looks like a blurry orange donut, not because the black hole itself emits light, but because the superheated material falling toward it glows brilliantly before crossing the event horizon and disappearing forever. When galaxies collide, it seems like it should be catastrophic. Billions of stars from one galaxy smashing into billions from another. But the reality is far gentler, at least for the stars themselves. Galaxies are mostly empty space, and when they merge, individual stars almost never actually collide. It's more like two clouds passing through each other, interpenetrating, mixing, but with the individual droplets, the stars, rarely touching. The distances between stars are simply too vast. In a typical region of a galaxy, stars are separated by several light years. That's trillions of kilometers of empty space between them. When two galaxies merge, stars from one pass through the space between stars in the other, their paths altered by gravity, but direct collisions extraordinarily rare. What does get disrupted are the orbits. Gravitational interactions between the two galaxies create tidal forces that pull and stretch both structures. Stars get flung into new orbits, some accelerated, some decelerated, their neat circular paths around the galactic center becoming elliptical or chaotic. Gas clouds collide and compress, triggering new waves of star formation. The overall structure of both galaxies changes, spiral arms get scrambled, and eventually the two galaxies merge into a single, usually elliptical galaxy. But from the perspective of an individual star system, a planet orbiting one of those stars, the collision might be almost imperceptible. The night sky would change over millions of years as new stars appeared, as the galaxy's structure evolved. There might be more supernovae as star formation increased, but day-to-day life? It would continue much as before. The collision is dramatic on cosmic scales, but gentle on stellar scales, a violence of structure, rather than direct impact. The spiral arms of galaxies like the Milky Way aren't fixed structures. Individual stars don't stay in the same spiral arm for their entire lives. Instead, spiral arms are density waves, regions where stars and gas are temporarily more concentrated, like a traffic jam on a highway. The jam moves, but the cars in it change. As stars orbit the galactic center, they pass through spiral arms, temporarily becoming part of that denser region before emerging from the other side and continuing their orbit. While they're in the arm, they're surrounded by more stars, more gas, and dust. If they're the right type of star, this might trigger new star formation from the compressed gas. Then they emerge from the arm into quieter space, continuing their journey. The spiral pattern itself rotates, but at a different speed than the star's orbit. The density wave pattern speed and the stellar orbital speed are different, which is why stars can enter and leave arms. It's a subtle and beautiful piece of galactic dynamics, discovered through careful observations and sophisticated modeling of how gravity shapes, galactic structure. Think of it like a wave on the ocean. The wave moves across the water's surface, but the water molecules themselves mostly just bob up and down. They don't travel with the wave. Similarly, spiral arms move through the galaxy, but the stars stay in their orbits, passing through the arms rather than being carried along by them. It's structure without substance, pattern without permanent membership, a rotating framework through which the galaxy's stars pass like guests at an eternal cosmic dance. About 85% of all matter in the universe is something we've never directly detected. We call it dark matter, and we know it exists only through its gravitational effects. It doesn't emit light, doesn't absorb light, doesn't interact electromagnetically at all, as far as we can tell. It's invisible, intangible, detectable only through the way it pulls on things we can see. The evidence for dark matter is overwhelming. Galaxies rotate faster than they should based on their visible matter. The outer regions should fly apart if only the stars and gas we see were providing gravity. Galaxy clusters are held together by far more gravity than their visible matter can provide. Gravitational lensing, the bending of light by gravity, shows us that there's much more mass present than we can see in stars and gas. So we know something is there, something with mass, something that exerts gravitational attraction. But what is it? Physicists have proposed various candidates: WIMPs, weakly interacting massive particles; axions, sterile neutrinos; primordial black holes; modified gravity theories. Experiments deep underground and in space are searching for dark matter particles, trying to detect them directly as they pass through our detectors. So far, nothing conclusive. It's humbling to realize that most of the matter in the universe is something we don't understand, something that doesn't interact with light or regular matter except through gravity. We're like people trying to understand the ocean by studying only the white caps on waves, seeing just the tiny visible fraction while most of the ocean remains hidden beneath the surface. The universe is far stranger and more mysterious than our everyday experience suggests. Galaxies come in a remarkable variety of shapes. Some, like the Milky Way, are elegant spirals with sweeping arms. Others are elliptical, smooth, featureless clouds of stars with no discernible structure, ranging from nearly spherical to elongated football shapes. Still others are irregular, lacking any clear pattern, their stars distributed in chaotic, asymmetric ways. These shapes tell stories. Spiral galaxies are typically younger, actively forming stars, with plenty of gas and dust organized into rotating disks. Elliptical galaxies are often older, having exhausted most of their gas, containing mostly old stars. They're often the products of galaxy mergers. When two spiral galaxies collide, the result is frequently an elliptical galaxy. Their organized spiral structures scrambled into a smooth, featureless blob. Irregular galaxies are often small, and many have been disrupted by gravitational interactions with larger neighbors. The Magellanic Clouds, visible from the southern hemisphere, are irregular galaxies being gradually torn apart by the Milky Way's gravity. They're like cosmic shipwrecks, their structures damaged by tidal forces, their stars and gas being slowly stripped away. Each galaxy's shape reflects its history, its formation, its interactions with neighbors, its age and evolution. By studying galaxies of different types, astronomers piece together the story of how galaxies form and evolve over cosmic time. It's detective work on the grandest scale, reading the shapes of distant galaxies like forensic evidence, deducing what must have happened to create what we see today. In 1995, astronomers pointed the Hubble Space Telescope at a tiny, apparently empty patch of sky near the Big Dipper. The region was about the size of a grain of sand held at arm's length. They left the telescope pointed there for 10 days, collecting light, building up an image from what seemed to be empty darkness. The result was astounding. In that tiny patch of sky, Hubble revealed about 3,000 galaxies. Not stars, galaxies, each one containing billions or hundreds of billions of stars. In that minuscule region that appeared empty to every previous telescope, there were thousands of entire galaxies, most of them so distant that their light had been traveling for billions of years to reach us. This image, called the Hubble Deep Field, revolutionized our understanding of the universe's scale. If a random patch of apparently empty sky contained 3,000 galaxies, then the entire sky must contain an incomprehensible number. Based on the deep field and subsequent observations, astronomers now estimate there are roughly 2 trillion galaxies in the observable universe. 2 trillion galaxies, each containing billions of stars, each star potentially hosting planets. The numbers become so large they lose meaning, becoming abstractions rather than quantities we can truly grasp. But the deep field made those abstractions visible, showing us in one image that the universe is vaster, more populated, more full of structure and complexity than we had imagined. And it did so by looking at what appeared to be nothing, revealing that in the universe there is no true emptiness. Everywhere we look, no matter how dark it seems, there are galaxies. Galaxies aren't distributed randomly throughout the universe. If you map their positions on large scales, a pattern emerges, a cosmic web of filaments and sheets, with galaxies clustered along these structures and enormous voids between them. It's like a three-dimensional spider web stretching across the universe, with galaxies strung along the threads. These filaments can be hundreds of millions of light years long, containing thousands of galaxies, all interconnected by gravity and the dark matter that pervades them. Where filaments intersect, you find galaxy clusters, dense collections of hundreds or thousands of galaxies. And between the filaments are the voids, vast regions containing very few galaxies, sometimes stretching 100 million light-years or more across. This structure formed through gravitational collapse. In the early universe, matter was distributed almost uniformly, with only tiny density variations. But over billions of years, gravity amplified these variations. Denser regions attracted more matter, becoming denser still, eventually forming the filaments we see. The voids formed where matter was slightly less dense. As gravity pulled material toward the filaments, it left these regions increasingly empty. The cosmic web is the largest known structure in the universe. It's the architecture of the cosmos on its grandest scale, the framework within which everything else exists. Our galaxy is part of a filament. Our local group of galaxies sits within a larger structure called the Virgo supercluster, which itself is part of the even larger Laniakea supercluster. We're not just in a galaxy or a group or a cluster. We're threads in a vast cosmic tapestry, connected to structures spanning hundreds of millions of light years. The Virgo supercluster is an immense structure containing our Milky Way, along with thousands of other galaxies, all loosely bound by gravity. It spans about 110 million light years across. To put that in perspective, if you could travel at the speed of light, the fastest possible speed in the universe, it would take you 110 million years to cross from one side to the other. The Milky Way sits in a relatively sparse region of this supercluster, in what's called the Local Group, a small collection of about 80 galaxies, most of them dwarfs, with the Milky Way and Andromeda being the two largest members. We're on the outskirts of the Virgo supercluster, far from its dense central region, where the Virgo cluster, containing over 2,500 galaxies, resides. But even the Virgo supercluster isn't the full story. Recent observations have revealed that it's part of an even larger structure called the Laniakea supercluster, which spans about 520 million light years and contains roughly 100,000 large galaxies. The name Laniakea comes from Hawaiian, meaning immense heaven, which seems appropriate for something so vast, and we're moving through this structure. The Milky Way isn't stationary. It's being pulled toward a region of space called the Great Attractor, a gravitational anomaly, somewhere in the direction of the constellations Triangulum, Australe, and Norma. There's also something beyond that called the Shapley supercluster that seems to be pulling on our local region of space. We're falling slowly toward these distant concentrations of mass, part of cosmic flows that operate on scales of hundreds of millions of light years. Quasars are the brightest objects in the universe. They're powered by matter falling into supermassive black holes at the centers of galaxies, and they can be so luminous that a single quasar outshines all the stars in its host galaxy combined. The brightest quasars emit as much energy as 100 trillion suns. From billions of light years away, they're still visible as bright points of light in our telescopes. The name quasar is short for quasi-stellar radio source. When they were first discovered in the 1960s, they appeared as star-like points, but emitted strong radio waves, which was unusual. It took years for astronomers to understand what they were seeing. The breakthrough came when they measured the redshifts of quasars and realized they were incredibly distant, which meant they had to be incredibly luminous to appear as bright as they did. We now understand that quasars are a type of active galactic nucleus, a galaxy whose central black hole is actively feeding, consuming vast amounts of matter. As gas spirals into the black hole, it heats up to millions of degrees, emitting enormous amounts of radiation across the electromagnetic spectrum. Some of this material gets channeled into jets that shoot out perpendicular to the accretion disk, creating beams of particles and energy that can extend for thousands of light years. Quasars were much more common in the early universe than they are today. This makes sense. Young galaxies had more available gas to feed their central black holes. As galaxies aged and used up their gas in star formation, or had it blown away by stellar winds and supernovae, the quasars went quiet. So when we look at distant quasars, we're seeing the universe in its youth, when galaxies were still growing and their central black holes were still gorging themselves on available matter. The most distant galaxies we can see appear as they were over 13 billion years ago, when the universe was less than 1 billion years old. We're literally looking back in time, seeing these galaxies as infants, just formed, vastly different from the mature galaxies we see nearby today. These early galaxies are smaller, more irregular, more chaotic than modern ones. They're forming stars at prodigious rates. sometimes creating hundreds of solar masses worth of new stars every year. They're rich in gas and dust, the raw materials of star formation. They haven't yet settled into the neat spiral or elliptical forms we see in the local universe. The James Webb Space Telescope, launched in 2021, has been specifically designed to study these distant early galaxies. Its infrared instruments can peer through dust and detect the stretched, red-shifted light from galaxies formed when the universe was just a few 100 million years old. Some of its early observations have surprised astronomers, finding galaxies that appear more massive and mature than theoretical models predicted they should be at such early times. This is the beauty of observational astronomy. Light takes time to travel, which means looking farther away is equivalent to looking farther back in time. We can't time travel, can't visit the past directly, but we can observe it. Every photon from a distant galaxy is a messenger from the past, carrying information about conditions billions of years ago. By studying galaxies at different distances, and therefore different ages, we can trace the history of galaxy formation and evolution, watching how the universe has changed over cosmic time. Elliptical galaxies are smooth, featureless, and reddish in color. Unlike spiral galaxies with their elegant arms and blue young stars, elliptical galaxies appear as diffuse ellipsoidal glows, filled mostly with old, red stars. They're the retirement homes of the cosmic city, places where the action has largely ceased, where the frenetic pace of star formation has slowed to nearly nothing. These galaxies have used up or lost most of their gas. Without gas, you can't form new stars, so the galaxies slowly redden over time as the hot, blue, short-lived stars die off, and only the cooler, redder, longer-lived stars remain. There's no ongoing star formation, no stellar nurseries, no young stars to speak of, just ancient stars slowly orbiting the galaxy's center, their orbits randomly oriented rather than organized into a rotating disk like spiral galaxies have. Many elliptical galaxies are the products of galaxy mergers. When two spiral galaxies collide, their organized structures get scrambled. The resulting galaxy is often elliptical, its gas used up in a burst of star formation triggered by the collision, its stars thrown into random orbits by the gravitational chaos. Giant elliptical galaxies often sit at the centers of galaxy clusters, having grown fat by cannibalizing smaller neighbors over billions of years. But elliptical galaxies aren't entirely dead. They still have supermassive black holes at their centers, and occasionally one will swallow a small galaxy or a large gas cloud, triggering a brief period of activity. They still undergo stellar evolution. Their stars still age and die, creating planetary nebulae and supernovae. But compared to star-forming spirals, ellipticals are quiet, calm, places where the universe's youth and vigor have given way to a slower, more sedate old age. Some galaxies have centers that blaze with extraordinary luminosity. These are called active galactic nuclei, or AGN. They're powered by supermassive black holes that are actively feeding, consuming gas, dust, and even entire stars, converting the potential energy of that infalling matter into radiation that can outshine billions of stars. The material falling toward the black hole doesn't plunge straight in. It forms an accretion disk, a swirling vortex of superheated matter spiraling inward. As particles in the disk rub against each other, friction heats them to millions of degrees. At these temperatures, matter emits strongly in X-rays, and ultraviolet light. Near the black hole's event horizon, velocities approach the speed of light, creating extreme relativistic effects. Some AGN produce jets, narrow beams of particles and energy shooting out perpendicular to the accretion disk. These jets can extend for thousands or even hundreds of thousands of light years, far beyond the host galaxy itself. They're powered by the black hole's rotation and magnetic fields, threading through the accretion disk, channeling material and energy outward at nearly the speed of light. Different types of AGN, quasars, blazars, Seyfert galaxies, radio galaxies, are probably all the same phenomenon seen from different angles or in different states of activity. A quasar is an AGN seen face-on, with the disk and jets pointed roughly toward us. A radio galaxy might be seen edge-on. The underlying physics is the same. Only our viewing angle differs. It's a reminder that classification systems in astronomy often reflect our perspective as much as any intrinsic differences in the objects themselves. Dwarf galaxies are the smallest, faintest galaxies, containing as few as 1,000 stars in the smallest cases. They're the cosmic equivalent of small towns, modest, easily overlooked, but far more numerous than their larger cousins. For every giant galaxy like the Milky Way, there might be hundreds or thousands of dwarf galaxies scattered throughout the universe. Many dwarf galaxies orbit larger galaxies as satellites. The Milky Way has dozens of known dwarf galaxy satellites, with names like the Sagittarius Dwarf Elliptical Galaxy, the Fornax Dwarf, the Sculptor Dwarf. Most are small, dim collections of old stars, containing little gas and forming few, if any, new stars. They're being slowly torn apart by the Milky Way's gravity, their stars gradually stripped away and absorbed into the larger galaxy. Some dwarf galaxies are more active. Dwarf. Irregular galaxies can have bursts of star formation, their limited gas supplies igniting periodically to create new generations of stars. These bursts can be triggered by interactions with other galaxies or by the compression of gas through the galaxy's own dynamics. Despite their small size, dwarf galaxies are important to our understanding of galaxy formation. Current cosmological models predict that large galaxies like the Milky Way formed through the merger of smaller proto-galaxies over time. Dwarf galaxies might be examples of these building blocks, galaxies that never merged with others and remained small. Studying them gives us insights into the early stages of galaxy formation, helping us understand how the universe's structure evolved from simple beginnings to the complex hierarchy of structures we see today. The Large Magellanic Cloud is a small galaxy visible from the southern hemisphere as a hazy patch of light. It's one of the Milky Way's satellite galaxies, orbiting our galaxy at a distance of about 160,000 light years. It's close enough that we can resolve individual stars within it, study star-forming regions in detail, observe supernovae and their remnants. It's a natural laboratory for astronomy, a galaxy near enough to study closely, but far enough away that we can see it in its entirety. But the Large Magellanic Cloud is in trouble. The Milky Way's gravity is pulling on it, distorting its structure, stripping away streams of gas and stars. These tidal effects are visible as the Magellanic Stream, a ribbon of gas stretching across the sky, trailing behind the galaxy as it orbits. In a few billion years, the Large Magellanic Cloud will likely be completely absorbed into the Milky Way, its stars and gas becoming part of our galaxy. The galaxy has a rich history of star formation. the Tarantula Nebula, located within the Large Magellanic Cloud, is one of the most active star-forming regions known, creating stars at a rate rarely seen elsewhere. In 1987, a massive star in the Large Magellanic Cloud exploded in a supernova, SN 1987A, the closest supernova observed in nearly 400 years. It was bright enough to be visible to the naked eye and provided an unprecedented opportunity to study a supernova in detail. The Large Magellanic Cloud reminds us that galaxies aren't isolated islands. They interact, influence each other, sometimes merge. The cosmic landscape is dynamic, with galaxies constantly affecting their neighbors through gravity, sometimes subtly, sometimes catastrophically. Nothing in the universe is truly alone. Galaxies existed when the universe was less than 1 billion years old. This is somewhat surprising. It means that within just a few 100 million years after the Big Bang, matter had already organized itself into the structures we recognize as galaxies. The universe worked quickly, pulling together clumps of dark matter and ordinary matter through gravity, creating the first stars, the first stellar clusters, and eventually the first galaxies. These early galaxies were small and irregular by today's standards. They hadn't yet grown through mergers into the massive spirals and ellipticals we see in the nearby universe. But they were vigorously forming stars, sometimes at rates that seem impossibly high compared to modern galaxies. They were building themselves up, creating stars that would later become the ancient, stellar populations we see in old galaxies today. The James Webb Space Telescope has been particularly valuable for studying these early galaxies. Some of its observations have shown galaxies that are more massive and more mature than expected for such early times, challenging our theories of how quickly galaxies can form and evolve. This is science at its best. Observations surprising us, forcing us to reconsider our models, pushing us toward a deeper understanding. The formation of the first galaxies marked a crucial transition in the universe's history. Before galaxies, space was filled with mostly diffuse gas, hydrogen and helium from the Big Bang, with tiny traces of lithium and beryllium. With galaxies came the first significant star formation, which led to the creation of heavier elements through fusion and supernovae. Galaxies were the engines that began enriching the universe with the chemical diversity we see today, transforming the primordial simplicity into something more complex, more structured, more interesting. The observable universe is everything we can theoretically see, a sphere centered on Earth with a radius of about 46.5 billion light-years in every direction. Wait, you might think, if the universe is only 13.8 billion years old, shouldn't light have only traveled 13.8 billion light-years? That's where cosmic expansion comes in. While light has been traveling for 13.8 billion years, the space through which it traveled has been expanding the entire time. An object that emitted light 13.8 billion years ago was much closer to us then. But in the time it took that light to reach us, that object has been carried away by cosmic expansion. It's now about 46.5 billion light-years away. So the observable universe's radius is much larger than the age of the universe times the speed of light. This means the observable universe contains an enormous volume of space, roughly 4x10 or 80 cubic meters, filled with an estimated 2 trillion galaxies. But here's the truly mind-bending part. The observable universe is almost certainly just a tiny fraction of the total universe. Beyond our observational horizon, space continues, possibly infinitely. There could be infinitely more galaxies out there that we'll never see because their light hasn't had time to reach us yet, and, due to accelerating expansion, never will. So when we talk about the universe, we're really talking about our observable universe, our cosmic neighborhood, the region of space that's causally connected to us, that we can in principle detect and study. Beyond that lies a vast unknown, regions of space that exist but that we can never observe, never interact with, never know anything about. The universe might be infinite or it might be finite, but larger than the observable portion. We don't know, and we may never know. Einstein's general relativity predicts that massive objects bend space-time, and light follows that curved space-time. This means that very massive objects, galaxy clusters, for instance, can act like cosmic magnifying glasses, bending and focusing light from more distant objects behind them. This effect is called gravitational lensing. Sometimes the lensing creates multiple images of the same distant object, arranged around the lensing mass. Sometimes it creates Einstein rings, complete circles of light where a distant galaxy is directly behind the lensing object. Sometimes it simply distorts and magnifies the background object, making faint, distant galaxies visible that would otherwise be too dim to detect. Gravitational lensing has become a powerful tool in astronomy. It allows us to study galaxies that formed when the universe was very young, using intervening galaxy clusters as natural telescopes to magnify them. It allows us to map the distribution of dark matter, since dark matter's gravity also causes lensing, even though we can't see the dark matter directly. And it allows us to measure distances and masses across the universe with precision that would be impossible otherwise. The Hubble Space Telescope and now the James Webb Space Telescope have captured spectacular images of gravitational lensing, arcs and rings of distorted light surrounding massive galaxy clusters, each arc a distant galaxy magnified and stretched by the cluster's gravity. These images are beautiful in their own right, but they're also windows into the distant universe, views that wouldn't be possible without gravity's ability to bend light and space itself. As of 2024, astronomers have confirmed over 5,600 exoplanets, planets orbiting stars beyond our solar system. This number grows regularly, sometimes by the week, as new detection methods improve and more data is analyzed. Just a few decades ago, we had no confirmed exoplanets at all. The first was discovered in 1992, orbiting a pulsar. The first planet found around a sun-like star came in 1995. Now we know of thousands, and statistical studies suggest that planets are extraordinarily common. There are likely more planets than stars in our galaxy. This discovery has fundamentally changed our perspective on the universe. We now know that our solar system isn't unique or special. Planets are the rule, not the exception. Almost every star you see in the night sky probably has planets orbiting it. Some have one, some have many. They come in sizes ranging from smaller than Earth to larger than Jupiter. They orbit at distances from their stars that range from practically touching to hundreds of astronomical units away. The methods we use to find these planets are ingenious. The transit method watches for tiny dips in a star's brightness when a planet passes in front of it. The radial velocity method detects the subtle wobble in a star's motion caused by an orbiting planet's gravity. Direct imaging actually photographs planets. Though this is difficult and only works for large planets orbiting far from bright stars. Gravitational microlensing detects planets through their gravitational effects on light from background stars. Each discovery adds to our understanding of how planetary systems form and evolve. We've found planets in places we didn't expect. Hot Jupiters orbiting closer to their stars than Mercury orbits our Sun. Planets around binary stars, planets orbiting dead stars. The universe's creativity in forming planetary systems seems boundless, and we're only beginning to catalog and understand this diversity. Some exoplanets orbit their stars so closely that their year lasts less than an Earth day. These are called hot Jupiters, gas giant planets that somehow ended up in extremely tight orbits, circling their stars in mere hours or days, their atmospheres heated to thousands of degrees by their proximity to their suns. Hot Jupiters were among the first exoplanets discovered because they're relatively easy to detect. Their large size creates noticeable stellar wobbles and significant transit signals. But they were also surprising because planets like Jupiter can't form that close to a star. It's too hot. The intense stellar radiation would prevent gas from accumulating. So these planets must have formed farther out and then migrated inward, either through interactions with the protoplanetary disk or through gravitational interactions with other planets that flung them inward. The conditions on hot Jupiters are extreme beyond imagination. Surface temperatures can exceed 2,000 degrees Celsius, hot enough to vaporize rock and metal. Some are tidally locked, with one side perpetually facing the star and the other in eternal darkness, creating temperature differences that drive winds reaching thousands of kilometers per hour. On some, it might rain liquid iron or glass. Their atmospheres contain vaporized metals, exotic compounds that exist nowhere in our solar system. These worlds challenge our understanding of planetary formation and evolution. They show us that planetary systems can be far more dynamic and chaotic than our relatively stable solar system suggests. Planets can migrate vast distances. They can be ejected entirely from their systems. They can end up in orbits and conditions that seem impossible. The universe, it turns out, creates planets in ways we're still struggling to understand, pushing them into configurations that test the limits of what planetary science thought possible. The TRAPPIST-1 system is remarkable. It contains 7 Earth-sized planets orbiting a single star, and 3 of those planets orbit in what's called the habitable zone, the region where temperatures might allow liquid water to exist on a planet's surface. The star itself is a red dwarf, much smaller and cooler than our Sun, which means the habitable zone is much closer in. All 7 planets orbit closer to their star than Mercury orbits our Sun, yet some might still be temperate enough for life. The system is just 40 light-years away, practically next door in cosmic terms. If we had a spacecraft that could travel at the speed of light, we could reach it in a human lifetime. Of course, we don't have such spacecraft, but the proximity means we can study these planets in detail. Telescopes can analyze the starlight passing through the planet's atmospheres during transits, looking for chemical signatures that might indicate habitability, or even life. What would it be like to stand on one of the TRAPPIST-1 planets? The star would appear about 3 times larger in the sky than our Sun appears from Earth, but dimmer, glowing with a deep red color. Because the planets are close together and close to their star, you might be able to see other planets in the system easily, some appearing larger in the sky than the moon appears from Earth. The sky might often contain multiple planets visible simultaneously, some showing crescents, some full, creating a celestial spectacle unlike anything visible from Earth. The discovery of TRAPPIST-1 suggests that multi-planet systems are common, and that Earth-sized planets in habitable zones might be abundant throughout the galaxy. Each discovery like this increases the odds that life exists elsewhere, that we're not alone in the universe. It doesn't prove anything. We still have no confirmed detection of life beyond Earth, but it makes the possibility seem more plausible, more likely, more within reach. Not all planets orbit stars. Some drift through space alone, unbound to any stellar system, wandering through the darkness of interstellar space. These are called rogue planets, and they're difficult to detect because they emit almost no light of their own. We find them mostly through gravitational microlensing. When one passes between us and a distant star, its gravity briefly magnifies the star's light, creating a detectable signal. How do planets become rogues? Most likely, they're ejected from their birth systems through gravitational interactions. During a solar system's chaotic early history, planets can gravitationally scatter each other, and sometimes one gets flung out entirely, sent on a one-way journey into the void. Or perhaps some form as solitary objects in interstellar clouds, though this is debated. These lonely worlds experience conditions almost unimaginably different from planets in our solar system. Without a sun, they receive no sunlight, no warmth from stellar radiation. Surface temperatures would be only a few degrees above absolute zero, perhaps warmed slightly by residual heat from formation or radioactive decay in the core. Any atmosphere would likely freeze solid onto the surface. If there were oceans, they'd be frozen kilometers deep. Yet some scientists speculate that under thick ice shells, subsurface oceans might exist, kept liquid by geothermal heat from the planet's core. These would be oceans in eternal darkness, cut off from any external energy source, but possibly warm enough to harbor microbial life if the right chemistry were present. It's speculative, perhaps unlikely, but it expands our thinking about where life might exist. Not every habitable world needs a sun. Some might carry their own heat within, needing nothing from the cosmos except the elements they're made of, and time for chemistry to work its slow magic. Fast radio bursts are mysterious millisecond-long flashes of radio waves from across the cosmos. They were first detected in 2007 when astronomers analyzing old data from the Parkes Radio Telescope in Australia noticed a peculiar signal, a brief, intense burst of radio energy lasting just a few milliseconds. Since then, hundreds more have been detected, and we still don't fully understand what causes most of them. The bursts are extraordinarily energetic. In just a few milliseconds, a fast radio burst can release as much energy as the sun emits in days or weeks. The fact that we can detect them from billions of light years away testifies to their incredible luminosity. Some repeat, the same source flashing multiple times, sometimes regularly, sometimes unpredictably. Others appear just once and never again. Theories about their origin include magnetars having starquakes, colliding neutron stars, evaporating black holes, or even more exotic possibilities. In recent years, astronomers have made progress by localizing some bursts to specific galaxies and even identifying repeating sources, which has helped narrow down the possibilities. But for many fast radio bursts, the mystery remains. There's something appealing about this mystery, isn't there? Even with all our sophisticated instruments and theoretical understanding, the universe can still surprise us with phenomena we don't immediately understand. Fast radio bursts remind us that we haven't figured everything out, that there are still discoveries waiting to be made, still cosmic events whose mechanisms remain puzzling. The universe keeps some secrets, revealing them slowly, making us work to understand what we're seeing. In September 2015, the LIGO detectors in Louisiana and Washington state detected something extraordinary, a gravitational wave, a ripple in the fabric of space-time itself, created by the collision of two black holes 1.3 billion light-years away. This was the first direct detection of gravitational waves, confirming a prediction Einstein had made a century earlier in his general theory of relativity. Gravitational waves are distortions in space-time, created by accelerating massive objects. When two black holes spiral toward each other and merge, they create powerful gravitational waves that propagate outward at the speed of light, alternately stretching and squeezing space itself as they pass. The effect is tiny. LIGO detected a change in distance of about 1/10,000th the width of a proton, but detectable with incredibly precise instruments. Since that first detection, LIGO and other gravitational wave observatories have detected dozens of events: black hole mergers, neutron-star mergers, and possibly other exotic collisions. Each detection provides information about the masses and spins of the merging objects, their distance from us, and the nature of extreme gravity itself. Gravitational wave astronomy is still in its infancy, but it's already revolutionizing our understanding of the universe. What makes gravitational waves special is that they provide a completely different way of observing the cosmos. Traditional astronomy relies on electromagnetic radiation, light, radio waves, X-rays, but many events don't produce much electromagnetic radiation. Black hole mergers, for instance, can be invisible to traditional telescopes. Gravitational waves let us hear these events, detecting the space-time ripples they create. It's like gaining a new sense, a way of perceiving the universe that was completely unavailable to us before 2015. The cosmic microwave background radiation is the afterglow of the Big Bang, visible in every direction we look. It's ancient light, released when the universe was just 380,000 years old, when it cooled enough for atoms to form and light to travel freely for the first time. That light has been traveling ever since, stretched by cosmic expansion from visible and ultraviolet wavelengths into microwaves, bathing the entire universe in a faint, nearly uniform glow. The CMB was discovered accidentally in 1964 by Arno Penzias and Robert Wilson, who were trying to eliminate persistent noise from their radio antenna at Bell Labs. They found a signal that came from all directions equally, with a temperature of about 3 Kelvin, 3 degrees above absolute zero. This was exactly what Big Bang theory predicted should exist, and its discovery was one of the key pieces of evidence that established the Big Bang as the correct model of cosmic origins. But the CMB isn't perfectly uniform. There are tiny temperature variations, about 1 part in 100,000, that represent the seeds of all structure in the universe. Regions that were slightly denser and hotter became the places where gravity eventually pulled matter together to form galaxies, and galaxy clusters. Regions that were slightly less dense became the voids. The pattern of these fluctuations encodes information about the universe's composition, age, geometry, and fate. Satellites like COBE, WMAP, and Planck have mapped the CMB in exquisite detail, measuring its temperature variations across the entire sky. These measurements have given us our most precise values for cosmological parameters. The universe's age, 13.8 billion years. Its composition, about 5% ordinary matter, 27% dark matter, 68% dark energy. And its geometry, flat, meaning parallel lines stay parallel on cosmic scales. The CMB is a baby picture of the universe, showing us what it looked like in its infancy, before stars and galaxies existed, just primordial light and matter beginning their long journey toward complexity. When two neutron stars collide, they create a kilonova, an explosion that produces heavy elements through rapid neutron capture. Gold, platinum, uranium, elements heavier than iron that can't be created in normal stellar fusion, are forged in these violent events. The neutron-rich environment allows atomic nuclei to capture neutron after neutron in rapid succession, building up heavier and heavier elements before they have time to decay. In August 2017, astronomers detected gravitational waves from a neutron star merger, and for the first time, they also detected the electromagnetic counterpart, the light from the kilonova. Telescopes around the world swung into action, observing the event across the spectrum from gamma rays to radio waves. The observations confirmed theoretical predictions. The light showed signatures of heavy elements being created, validating the idea that neutron star mergers are major sources of the universe's gold and platinum. This means the gold in any ring or necklace was likely created in the death throes of neutron stars billions of years ago, in some ancient collision that released more energy in a few seconds than the sun will emit in its entire lifetime. Those atoms were then scattered into space, eventually becoming part of the molecular cloud that collapsed to form our solar system. They drifted through space for eons before ending up in the Earth's crust, where they were mined, refined, and shaped into jewelry. It's a remarkable story of cosmic recycling. Nothing is created from nothing. Everything has a history. The elements in your body, the materials around you, all have cosmic origins, forged in stars or stellar collisions, scattered across space, gathered together again by gravity to form planets, and eventually us. We're not just in the universe, we're made of it, assembled from debris that's been cycling through cosmic processes for billions of years. The universe is expanding. This isn't just a theory, it's an observed fact. Distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This relationship was first discovered by Edwin Hubble in the 1920s and is now called Hubble's law. It provided the first strong evidence that the universe had a beginning, that space itself is expanding, carrying galaxies apart like raisins in rising bread dough. The expansion doesn't mean galaxies are moving through space. It means space itself is stretching. Imagine drawing dots on a balloon and then inflating it. The dots move apart not because they're traveling across the balloon's surface, but because the surface itself is expanding. Similarly, galaxies aren't flying through space away from each other. The space between them is increasing. This expansion has a profound implication. If the universe is expanding now, it must have been smaller in the past. Trace the expansion backward in time, and you reach a point where all the universe's matter and energy was compressed into an infinitesimally small, infinitely dense state. This is the Big Bang, not an explosion in space, but an explosion of space itself, the beginning of the universe as we know it. The expansion rate isn't constant. It's been changing throughout cosmic history. Surprisingly, recent observations show the expansion is accelerating. This acceleration, discovered in the late 1990s, was completely unexpected and has been attributed to dark energy, a mysterious force that seems to be pushing space apart. What dark energy is remains one of the biggest mysteries in physics. We know it exists through its effects, but we don't know what it's made of or why it has the properties it does. About 68% of the universe is dark energy, a mysterious force causing cosmic expansion to accelerate. This discovery came from observations of distant Type Ia supernovae in the late 1990s. Astronomers expected that the universe's expansion should be slowing down due to gravity pulling everything together. Instead, they found that distant supernovae were dimmer than expected, suggesting they were farther away than they should be if expansion were constant or decelerating. The universe's expansion is speeding up. This was so surprising, so contrary to expectations, that it took years of additional observations and analysis to confirm. But the evidence became overwhelming, and in 2011, the discovery earned a Nobel Prize. We now know with high confidence that not only is the expansion accelerating, but this acceleration has been increasing for the past several billion years. What is dark energy? We don't really know. The simplest explanation is that it's a property of space itself, Einstein's cosmological constant, which he originally introduced and then abandoned, but which now seems to actually exist. In this view, empty space has intrinsic energy, and as space expands, more space is created, which means more dark energy, which drives faster expansion in a reinforcing cycle. The implications are profound. If dark energy continues to dominate, the universe will expand forever, accelerating without limit. Galaxies outside our local group will eventually recede so fast that their light can never reach us. The universe will become increasingly empty from our perspective, with only our local gravitational neighbors remaining visible. Eventually, even the cosmic microwave background will fade away, redshifted beyond detectability. The universe will approach a state of maximum entropy, cold and dark and empty, with isolated islands of matter drifting in an ever-expanding void. It's a lonely fate, but one that still lies trillions of years in the future. The Boomerang Nebula, located about 5,000 light-years away in the constellation Centaurus, holds the distinction of being the coldest place we know of in the universe. Its temperature is about negative 272 degrees Celsius, just 1 degree above absolute zero. That's colder than the cosmic microwave background radiation, colder than the natural temperature of space itself, which hovers around negative 270 degrees Celsius. How can something be colder than the background temperature of the universe? The Boomerang Nebula is a planetary nebula, the expanding shell of gas expelled by a dying star. But in this case, the gas is expanding extraordinarily rapidly, at about 600,000 kilometers per hour. As gas expands, it cools, and the Boomerang Nebula's gas is expanding so fast that it's cooling to temperatures even lower than its surroundings. This cooling happens through a process similar to how a refrigerator works. When gas expands rapidly, it does work against its own pressure, which requires energy. That energy comes from the gas's thermal energy, so the temperature drops. In the Boomerang Nebula, this expansion cooling has created the coldest known, naturally occurring place in the universe. It's a strange thought, isn't it? In a universe filled with blazing stars, exploding supernovae, and matter falling into black holes at millions of degrees, the coldest place is this cloud of gas expanding in the darkness, cooling itself through its own motion, approaching the ultimate limit of coldness that physics allows. Even in death, even in expansion and dissipation, this stellar remnant achieves something extreme, something that stands out against the cosmic background. Some binary star systems contain a white dwarf stealing material from a companion star. As hydrogen accumulates on the white dwarf's surface, pressure and temperature increase until suddenly, whoosh, the accumulated hydrogen ignites in a thermonuclear explosion. This is called a nova, and for a few days or weeks, the system brightens dramatically, sometimes becoming visible to the naked eye before fading back to obscurity. The remarkable thing about some of these systems is that they repeat. The white dwarf survives the explosion. It's dense and massive enough that the blast doesn't destroy it. After the nova, it continues stealing material from its companion. The hydrogen piles up again, and eventually there's another explosion. These are called recurrent novae, and they can go off every few decades or centuries. One famous example is T Coronae Borealis, also called the Blaze Star, which has been observed having novae in 1866 and 1946, and is expected to have another outburst in the next few years. When it does, it will briefly become visible to the naked eye. A star suddenly appearing in the constellation Corona Borealis, where none was obvious before, then fading away again over several weeks. These systems represent a delicate balance. The white dwarf accretes material slowly, stores it, then releases it explosively. It's a cosmic cycle of accumulation and release, matter and energy flowing from one star to another and then out into space. And if the white dwarf accumulates enough mass over many cycles, it might eventually approach the Chandrasekhar limit and explode entirely in a type Ia supernova, ending the cycle permanently in one final, spectacular blast. Occasionally, a star wanders too close to a black hole. The tidal forces, the difference in gravitational pull between the near and far sides of the star, become so strong that they literally tear the star apart. The star is stretched into a long stream of gas, a process astronomers poetically call spaghettification. Some of this material falls into the black hole, heating up as it spirals inward, creating a brilliant flare that can outshine the entire galaxy for weeks or months. These events, called tidal disruption events or TDEs, are relatively rare, perhaps one per galaxy per 10,000 to 100,000 years. But in a universe with hundreds of billions of galaxies, they're happening somewhere all the time. Astronomers have now observed dozens of them, using telescopes that scan the sky repeatedly looking for transient events, sudden brightenings that indicate something dramatic is happening. Each TDE is unique. The details depend on the star's size and composition, the black hole's mass and spin, how close the star passes, and the angle of approach. Some stars are completely destroyed, all their material either falling into the black hole or being flung out into space. Others lose only their outer layers, with their cores surviving to continue orbiting, scarred but intact. There's something visceral about tidal disruption events, something that makes the black hole's power tangible. These aren't abstractions or mathematical curiosities. They're stars, objects like our sun, being ripped apart by gravity so strong that the difference in pull across a few million kilometers is enough to overcome all the star's structural integrity. It's gravity at its most violent, demonstrating that black holes aren't just empty voids, but active predators, capable of destroying anything that ventures too close. The James Webb Space Telescope, launched in December 2021, represents a new era in observational astronomy. Its infrared instruments can detect the stretched, redshifted light from the universe's first galaxies, formed just a few 100 million years after the Big Bang. It can peer through dust clouds that block visible light, revealing star-forming regions and planetary systems in formation. It can analyze the atmospheres of exoplanets, searching for chemical signatures that might indicate habitability or even life. Webb's primary mirror is 6.5 meters across, much larger than Hubble's 2.4-meter mirror, giving it far greater light-gathering power. And because it observes in infrared rather than visible light, it can see things Hubble can't. Infrared light passes through dust more easily, and the light from the most distant objects has been redshifted into the infrared by cosmic expansion. Webb is designed specifically to observe these distant, dusty, or cool objects that elude other telescopes. The telescope orbits the Sun at the second Lagrange point, about 1.5 million kilometers from Earth, where it's shielded from the Sun, Earth, and Moon by a tennis court-sized sunshield. This allows its instruments to cool to about 40 Kelvin, necessary for detecting faint infrared signals without being overwhelmed by the telescope's own heat. Webb's early observations have already yielded surprises, galaxies that appear more massive and mature than expected at early times, detailed views of star formation in nearby nebulae, spectacular images of planets in our solar system. It's only the beginning. Webb is designed to operate for at least 10 years, possibly longer, and each year will bring new discoveries, new insights, new views of the universe that were impossible before. We're in the early days of understanding what this telescope will teach us, but already it's clear that our view of the cosmos is being transformed. When NASA's OSIRIS-REx spacecraft approached asteroid Bennu to collect a sample, scientists expected a solid surface. What they found was far stranger. Bennu's surface was so loose and fluffy that the spacecraft's sampling arm sank in significantly when it touched down. If the spacecraft had lingered, it might have sunk in entirely, like stepping into deep snow or quicksand. Bennu is what's called a rubble pile asteroid, a collection of rocks and boulders held together loosely by gravity, with lots of empty space between the particles. It's not a solid chunk of rock, but more like a gravel pile in space. This structure probably formed when a larger asteroid was shattered by a collision, and the fragments came back together under their mutual gravity, but didn't pack tightly, leaving a highly porous structure. This discovery has implications for planetary defense. If we ever need to deflect an asteroid heading toward Earth, knowing its structure matters. A solid rock asteroid might respond predictably to an impact or gravitational tug. A rubble pile might respond differently, absorbing impacts, fragmenting unpredictably, or proving difficult to push or pull effectively. Understanding asteroid structure helps us prepare for scenarios we hope never to face. The sample OSIRIS-REx collected, about 250 grams of material from Bennu's surface, was returned to Earth in September 2023 and is now being analyzed in laboratories. This material is pristine, unchanged since the solar system's formation 4.6 billion years ago. It contains organic compounds, water-bearing minerals, and other materials that might tell us about the ingredients that were available when Earth formed, helping us understand how our planet became habitable and how life began. Saturn's small moon Enceladus sprays geysers of water ice into space from cracks near its south pole. These plumes were discovered by the Cassini spacecraft in 2005 and have been studied extensively since. They're not just water ice. They contain organic molecules, salts, and other compounds that suggest Enceladus has a liquid ocean beneath its icy crust, and that this ocean might be in contact with a rocky core where interesting chemistry could be happening. The plumes are dramatic. They shoot hundreds of kilometers into space, creating a torus of water ice particles around Saturn's orbit. In fact, they're the primary source of particles for Saturn's E-ring. Some of the ice falls back to Enceladus's surface as snow, while some escapes into orbit around Saturn. Cassini flew through these plumes multiple times, sampling their composition directly. The spacecraft detected hydrogen gas, which suggests hydrothermal activity on Enceladus's ocean floor, hot water reacting with rock, similar to hydrothermal vents on Earth's ocean floor. On Earth, such vents support rich ecosystems, raising the tantalizing possibility that Enceladus's ocean might harbor life. Enceladus is remarkably small, only about 500 kilometers in diameter, small enough that you could drive around it in less than 2 days. Yet this tiny moon has a global ocean, active geology, and organic chemistry. It's one of the most promising places in the solar system to search for life, and future missions are being planned to return there, perhaps to sample the plumes in more detail, or even to land and drill through the ice to reach the ocean below. If life exists elsewhere in our solar system, Enceladus is one of the places we're most likely to find it. In 2020, scientists announced the tentative detection of phosphine in Venus's clouds, a molecule that on Earth is primarily produced by life or industrial processes. The discovery was controversial from the start. Follow-up observations and reanalysis of the data have called the detection into question, with some studies confirming it and others finding no evidence of phosphine at all. Whether or not phosphine is truly present on Venus remains uncertain, but the announcement sparked renewed interest in Venus as a potentially habitable environment, or at least an interesting one from an astrobiological perspective. Venus's surface is hellish, hot enough to melt lead, with crushing atmospheric pressure. But higher in the atmosphere, around 50 to 60 kilometers up, conditions are much more temperate. Temperature and pressure are similar to Earth's surface, and droplets of sulfuric acid form clouds that might, just possibly, harbor microbial life. The idea of life in Venus's clouds isn't new. Carl Sagan proposed it decades ago, but the phosphine detection, however uncertain, brought the idea back into mainstream discussion. Could microbes be floating in Venus's atmosphere? Perhaps descendants of organisms that lived on Venus's surface billions of years ago, when the planet might have had oceans and a more temperate climate. We don't know. The phosphine detection might be a false positive, or it might be real but produced by unknown chemistry rather than biology. What the controversy demonstrates is how difficult it is to detect life at a distance, and how much we still have to learn about planetary atmospheres and chemistry. Venus remains a planet of mysteries, a world we've neglected for decades in favor of Mars and the outer planets, but which might reward renewed attention with discoveries we can't yet imagine. The Parker Solar Probe has traveled closer to the Sun than any human-made object, skimming through the Sun's outer atmosphere at distances where temperatures exceed 1,300 degrees Celsius. It's not melting because it's protected by a carbon composite heat shield that faces the Sun, reflecting and radiating away most of the heat while keeping the instruments behind it relatively cool, about room temperature. The probe's mission is to study the solar wind and the Sun's corona, the outer atmosphere that's mysteriously much hotter than the Sun's surface. The surface is about 5,500 degrees Celsius, but the corona reaches millions of degrees. Why? That's one of the questions Parker is helping to answer. Parker's trajectory involves multiple gravity assists from Venus, each one bringing the probe closer to the Sun. At its closest approaches, it's traveling at speeds exceeding 700,000 kilometers per hour, the fastest human-made object ever. At these speeds, it could travel from New York to Tokyo in less than a minute. The data Parker is collecting is revealing the Sun's behavior in unprecedented detail, measuring the solar wind's properties, detecting switchbacks in the magnetic field, observing solar energetic particle events up close. It's touching the Sun, not literally but effectively, sampling conditions in an environment that no spacecraft has visited before. Each close pass provides new data, new insights into our nearest star, helping us understand the Sun's behavior and its effects on Earth and the rest of the solar system. Many stars host multiple planets. Some systems are packed with planets orbiting much closer than Mercury orbits our Sun. Others have planets in wide orbits, farther than Neptune is from us. This diversity suggests that planetary system formation is a robust process, able to create many different configurations depending on initial conditions and subsequent evolution. The Kepler Space Telescope, which operated from 2009 to 2018, revolutionized our understanding of planetary systems by staring at a single patch of sky for years, monitoring the brightness of 150,000 stars simultaneously. It detected thousands of planetary transits, revealing that planets are extraordinarily common. Statistical analyses of Kepler's data suggest that, on average, there's at least one planet per star in our galaxy. Some systems resemble ours, rocky planets close in, gas giants farther out. Others are completely different, systems of super-Earths, planets larger than Earth but smaller than Neptune, a planet type that doesn't exist in our solar system but appears common elsewhere. Some systems have hot Jupiters, others have planets in eccentric, highly elliptical orbits. Still others have planets orbiting binary stars. This diversity challenges our theories of planet formation. We thought we understood how planets formed because we had one example, our solar system, and we built models to explain it. But now we know that our solar system is just one of many possible configurations, perhaps not even a typical one. Understanding why planets form in such varied ways, what determines whether a system ends up like ours or radically different, is one of the major questions driving current research in planetary science. In October 2017, astronomers detected an object moving through the solar system on a trajectory that clearly indicated it came from interstellar space. This was Oumuamua, the first confirmed interstellar object ever observed passing through our solar system. Its name, from Hawaiian, means scout, or messenger from afar arriving first. Oumuamua was strange from the beginning. It was highly elongated, perhaps 10 times longer than wide, with a shape unlike any asteroid or comet we'd seen before. It was tumbling as it moved, its light varying dramatically in a pattern suggesting an irregular shape. And most puzzling, it accelerated slightly as it left the inner solar system, more than could be explained by the sun's gravity alone. That acceleration sparked much debate. Comets accelerate due to outgassing. As they warm up, ice vaporizes and jets of gas push them slightly. But Oumuamua showed no signs of a cometary tail or coma. So what was causing the acceleration? Theories ranged from outgassing of more exotic ices that don't produce visible tails, to radiation pressure on an unusually flat, reflective object, to, more speculatively, artificial origins as a light sail or probe from an alien civilization. The alien hypothesis gained some attention but is considered unlikely by most astronomers. More probable explanations involve natural processes we don't fully understand yet. What Oumuamua demonstrated is that interstellar objects do pass through our solar system, probably regularly, and we now have the capability to detect them. Future surveys will likely find more, giving us samples, even if only glimpses, of planetary systems around other stars, debris that's been wandering the galaxy for who knows how long before briefly passing through our neighborhood. Here's a puzzle that keeps physicists awake at night. The universe shouldn't exist, or at least, it shouldn't exist in its current form. According to our understanding of particle physics, the Big Bang should have created equal amounts of matter and antimatter, and when matter and antimatter meet, they annihilate each other completely, converting their mass into pure energy. If the universe truly began with equal amounts of both, everything should have annihilated, leaving nothing but radiation. No atoms, no stars, no galaxies, no us. But clearly, that didn't happen. We exist. The universe is filled with matter. Somehow, there was a slight asymmetry. For every billion antimatter particles, there were 1,000,000,001 matter particles. When everything annihilated, that tiny excess remained, and it's what makes up everything we see today. Every atom in your body, every star in the sky, exists only because of this minuscule imbalance. Why was there this asymmetry? We don't know. It's one of the fundamental unsolved problems in physics. There are theories. Perhaps certain particle interactions violate something called CP symmetry in just the right way to create a matter excess. Perhaps there were exotic processes in the first moments after the Big Bang that favored matter over antimatter. But we don't have definitive answers, only speculations and ongoing experiments. This mystery is essential to our existence. If the universe had perfect symmetry between matter and antimatter, we wouldn't be here to wonder about it. The fact that we exist at all tells us that something broke that symmetry, that the universe played favorites with matter over antimatter. Understanding why remains one of the deepest questions we can ask about the nature of reality itself. Time passes at different rates depending on your speed and the strength of the gravitational field you're in. This isn't science fiction. It's a measured, verified consequence of Einstein's relativity. Astronauts on the International Space Station age slightly slower than people on Earth's surface. The difference is tiny, about 0.007 seconds over 6 months, but it's real and measurable. Two effects contribute to this. First, the astronauts are moving fast. The ISS orbits at about 7.7 kilometers per second, and special relativity says that moving clocks run slow. This effect would make astronauts age slower. But second, they're farther from Earth's center, in a weaker gravitational field. And general relativity says that clocks run faster in weaker gravity. This effect would make astronauts age faster. Both effects are happening simultaneously, and they partially cancel out. The speed effect is larger, so the net result is that astronauts age slightly slower than people on the ground. GPS satellites experience similar effects. They're moving fast, but are also in a weaker gravitational field than Earth's surface. Engineers have to account for both effects in GPS calculations, or the system would accumulate errors of several kilometers per day. Time dilation seems abstract, but it's not. It's measurable, practical, and essential to understand for any technology that requires precise timing. It also reminds us that time isn't absolute, isn't the same for everyone everywhere. Your personal clock, your experience of time, depends on how fast you're moving and how strong the gravitational field is around you. Time is local, personal, woven into the fabric of space-time itself, rather than being some universal background against which events unfold. Here's an idea that sounds like science fiction, but emerges from serious physics. The holographic principle suggests that all the information contained in a three-dimensional volume of space might actually be encoded on the two-dimensional boundary of that space. It's like a hologram, a two-dimensional surface that contains all the information needed to reconstruct a three-dimensional image. This principle emerged from studying black holes. Stephen Hawking and others discovered that a black hole's entropy, a measure of the information it contains, is proportional to the area of its event horizon, not its volume. This was surprising because normally the amount of information something contains scales with its volume. But for black holes, it scales with surface area, as if all the information about what fell into the black hole is somehow encoded on its surface. Physicists generalized this insight, suggesting that perhaps all of space works this way, that our three-dimensional universe might be described completely by information encoded on a distant two-dimensional boundary. This has profound implications for quantum gravity, the theory of everything physicists are seeking, and it suggests that space itself might be emergent, a kind of hologram projected from information encoded elsewhere. Does this mean we live in a simulation, a projection from some two-dimensional reality? Not exactly. The holographic principle is about information encoding, not about fundamental reality being illusory. But it does suggest that our intuitive picture of space as a three-dimensional container is incomplete. Space might be more subtle, more information-based than we imagine. It's a reminder that at the deepest levels, reality is strange, counterintuitive, and more information theoretic than our everyday experience suggests. About 94% of the universe is made of things we can't directly detect, dark matter and dark energy. Everything we can see, touch, measure directly, all the atoms, all the light, all the ordinary matter, makes up just 5% of the total. We're trying to understand a universe where almost everything is invisible to us, detectable only through indirect effects. Dark matter makes up about 27% of the universe. We know it's there because of its gravitational effects. Galaxies rotate too fast. Galaxy clusters contain more gravity than their visible matter provides. Light bends around galaxy clusters more than it should based on visible matter alone. But what is dark matter? We don't know. It doesn't interact electromagnetically, doesn't emit or absorb light. It might be particles we haven't discovered yet. It might be something more exotic. Despite decades of experiments, we haven't directly detected a single dark matter particle. Dark energy is even more mysterious. It makes up about 68% of the universe and is causing cosmic expansion to accelerate. We know even less about what it is. It might be a property of space itself, or it might be some field permeating the universe. We can measure its effects with increasing precision, but we have no idea what it fundamentally is. Think about that. We've mapped the universe, counted galaxies, measured cosmic expansion, and learned an enormous amount about how the cosmos works. But we're still fundamentally ignorant about what most of it is made of. We're like people trying to understand a forest by only studying the flowers. We can learn a lot, but we're missing the trees, the soil, the underground root systems that make up most of the ecosystem. The universe is far stranger than the visible portion suggests. Black holes aren't entirely black. Stephen Hawking discovered in the 1970s that black holes emit radiation due to quantum effects near the event horizon, a phenomenon now called Hawking radiation. This radiation causes black holes to slowly lose mass, eventually evaporating completely over unimaginably long timescales. The mechanism involves virtual particle-antiparticle pairs that quantum mechanics says are constantly popping into existence throughout space. Normally, these pairs quickly annihilate. But near a black hole's event horizon, one particle might fall in while the other escapes. To an outside observer, it looks like the black hole is emitting radiation and losing mass in the process. For stellar mass black holes, say 10 times the sun's mass, the Hawking radiation is incredibly faint, and the evaporation time is incredibly long, about 1067 years. That's 10 million trillion years, far longer than the current age of the universe. For supermassive black holes, the times are even longer. These black holes won't evaporate for countless eons, long after all the stars have burned out and the universe has grown cold and dark. But eventually, if we wait long enough, and we're talking time scales that make the current age of the universe seem like a blink, even black holes evaporate. They get smaller and hotter as they lose mass, radiating more intensely as they shrink, finally ending in a brief burst of radiation as the last bit of mass converts to energy. Black holes are temporary, given enough time. Nothing in the universe is truly eternal except, perhaps, space itself and whatever fundamental laws govern reality. Some interpretations of physics suggest our universe might be just one of many, perhaps infinitely many, in a vast multiverse. Different versions of multiverse theory propose different mechanisms. In eternal inflation, quantum fluctuations during the Big Bang create pocket universes with different properties. In the many worlds interpretation of quantum mechanics, every quantum measurement creates branching realities. In string theory, the vast landscape of possible vacuum states might all be realized somewhere. These ideas are controversial because they're difficult or impossible to test. How do you prove the existence of other universes if, by definition, they're causally disconnected from ours? Impossible to observe or interact with. Some physicists embrace multiverse ideas because they seem to emerge naturally from certain theories. Others reject them as untestable metaphysics, not science. The multiverse also offers a potential explanation for the apparent fine-tuning of physical constants in our universe. Many parameters, the strength of gravity, the mass of the electron, the cosmological constant, seem precisely calibrated to allow complex structures like galaxies, stars, and life. Change them even slightly, and the universe becomes inhospitable. In a multiverse, every possible combination of parameters is realized somewhere. We exist in a universe with life-permitting parameters, not because they were designed, but because we couldn't exist in universes with different parameters. It's an anthropic argument. We observe what we observe because we couldn't observe anything else. Is the multiverse real? We don't know. Maybe it's a profound insight into reality's structure. Maybe it's an untestable speculation that will fade as theories improve. Either way, it represents how far cosmology has pushed, attempting to answer questions about why the universe has the properties it does, about whether our universe is unique or one among many, about the ultimate nature of existence itself. Quantum entanglement creates connections between particles that persist regardless of distance. Measure one entangled particle, and you instantly know something about its partner, even if that partner is on the other side of the galaxy. The particles don't communicate. No information travels between them faster than light, but they're correlated in ways that have no classical explanation, ways that Einstein called spooky action at a distance. Einstein didn't like entanglement. He thought it revealed some incompleteness in quantum mechanics, that there must be hidden variables we're missing that explain the correlations without requiring instantaneous connections. But experiments have repeatedly confirmed that entanglement is real, that particles can be correlated in ways that violate classical locality, that quantum mechanics really does allow these strange connections. Entanglement isn't just a curiosity, it's being harnessed for technology. Quantum computers use entanglement to perform certain calculations faster than classical computers. Quantum cryptography uses entanglement to create communication channels that are provably secure against eavesdropping. We're learning to manipulate and control quantum states in ways that seemed like science fiction just decades ago. But entanglement also challenges our understanding of reality. It suggests that separability, the idea that distant objects are truly independent, isn't quite right at the quantum level. The universe is more interconnected, more holistic than classical physics suggested. Particles that interact become entangled, and that entanglement persists even after they separate. In a sense, nothing that has ever interacted is truly independent. The universe is woven together by quantum correlations, an invisible web of connections spanning space and time. The universe's geometry is remarkably flat. Parallel lines stay parallel. The angles of triangles sum to 180 degrees. The ordinary Euclidean geometry we learn in school applies on cosmic scales. But this flatness is puzzling because it requires an extraordinary fine-tuning of the universe's initial conditions. The universe's geometry is determined by its density. If density is above a critical value, the universe is positively curved, like the surface of a sphere. If below, it's negatively curved, like a saddle. If exactly at the critical density, it's flat. But here's the thing, a flat universe is unstable. Any tiny deviation from exact flatness grows over time. An early universe that was even slightly curved would become extremely curved as it evolved. Yet the universe today is flat to within measurement precision. For this to happen, the early universe's density must have been fine-tuned to extraordinary precision, something like 1 part in 1060. That's like balancing a pencil on its point and having it stay balanced for billions of years. It seems implausibly precise, which suggests we're missing something in our understanding. The leading solution to the flatness problem is inflation, a brief period of exponential expansion in the universe's first fraction of a second. Inflation stretches space so dramatically that any initial curvature gets flattened out, like inflating a balloon makes its surface appear flatter from the perspective of something on it. Inflation explains why the universe is flat without requiring fine-tuned initial conditions. But inflation itself raises questions. What caused it? What stopped it? How do we test it? The flatness problem is solved, perhaps, but only by introducing new mysteries to unravel. We don't know what existed before the Big Bang, or even if before is a meaningful concept. Time itself might have begun with the Big Bang, which means asking what came before is like asking what's north of the North Pole. The question doesn't make sense because there's no before if time didn't exist yet. Some theories suggest the universe is cyclic, that it undergoes endless cycles of expansion and contraction, with each Big Bang following a previous big crunch. Others propose that our universe budded off from a parent universe or emerged from a quantum fluctuation in a pre-existing space. Still others suggest that time is emergent, arising from more fundamental, timeless physics. The honest answer is that we don't know. We can trace the universe's history back to fractions of a second after the Big Bang, when conditions were hot and dense, but still describable by known physics. Before that, during the Planck epoch, the first 1043 seconds, we need a theory of quantum gravity that we don't yet have. What happened then or whether before even exists, remains speculation. This uncertainty doesn't diminish what we've learned. We understand the universe's evolution from 13.8 billion years ago to now in remarkable detail. We know how structure formed, how galaxies evolved, how the elements were created. But the ultimate origin, the first cause, the reason something exists rather than nothing, these remain mysteries. Perhaps they're answerable through physics, or perhaps they touch on questions that transcend science, questions about existence itself that no amount of data can fully resolve. The universe is vast and old. Our galaxy alone contains hundreds of billions of stars. Many have planets. Some of those planets orbit in habitable zones. If life is common, and if even a small fraction of life develops intelligence and technology, there should be many technological civilizations in the galaxy. Some should be millions or billions of years older than us. So why haven't we detected them? Where is everyone? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where are they?" There are many proposed solutions, Perhaps life is extraordinarily rare. Maybe Earth's particular combination of circumstances is unique or nearly so. Perhaps intelligence is rare, even if microbial life is common. Perhaps civilizations don't last long. They destroy themselves through war, environmental collapse, or other catastrophes before becoming spacefaring. Perhaps they exist but remain quiet, either deliberately avoiding contact or simply not broadcasting. Perhaps interstellar travel and communication are harder than we imagine. Or perhaps we're alone. Perhaps in all the vastness of the galaxy, we're the only technological civilization currently active. It's a lonely thought, but it might be true. We've only been listening for extraterrestrial signals for a few decades, a cosmic eye blink. We've only examined a tiny fraction of the galaxy. Absence of evidence isn't evidence of absence. The Fermi paradox reminds us how much we don't know about life's distribution in the universe. It's possible we'll detect a signal tomorrow, or we might search for centuries and find nothing. Either way, the question, are we alone, remains one of the most profound we can ask, touching on our place in the cosmos, the nature of intelligence and consciousness, and the ultimate fate of civilizations, including our own. Some physicists and philosophers have proposed that consciousness might play a role in quantum mechanics, particularly in what's called the measurement problem. In quantum mechanics, particles exist in superposition, multiple states simultaneously, until measured, at which point the superposition collapses into a single definite state. But what counts as a measurement? Does it require a conscious observer, or is any interaction sufficient? The Copenhagen interpretation, one of the oldest and most widely taught interpretations of quantum mechanics, seems to give consciousness a special role. It suggests that the act of observation causes the wave function to collapse. But this raises troubling questions. Was the universe in superposition before conscious beings evolved? Do different consciousness levels cause different degrees of collapse? Most physicists today don't think consciousness is truly necessary. Any interaction that records information, conscious or not, seems sufficient. Yet the questions persist. Why does observation change anything? What's the boundary between quantum and classical behavior? Some interpretations, like the many worlds interpretation, eliminate collapse entirely, suggesting that all outcomes occur in branching parallel realities. Others, like quantum Bayesianism, treat the wave function as representing knowledge rather than physical reality. The relationship between mind and matter, between consciousness and physical law, remains deeply mysterious. Quantum mechanics gives us extraordinarily accurate predictions about how particles behave, but it doesn't clearly tell us what's really happening, what the wave function represents, or why measurement seems special. These aren't just technical questions. They touch on the nature of reality itself, on what exists and how we know about it, on the relationship between the observer and the observed. Perhaps consciousness is irrelevant to quantum mechanics, or perhaps there's some deep connection we haven't understood yet. The universe appears to be geometrically flat, meaning that on the largest scales, the rules of Euclidean geometry apply. Parallel lines stay parallel. The angles of a triangle sum to exactly 180 degrees. Light travels in straight lines through space. This has been confirmed by measuring the cosmic microwave background and the large-scale distribution of galaxies. And the results consistently show that the universe's curvature, if it exists at all, is extraordinarily small. This flatness has profound implications for the universe's fate. A positively curved universe, like the surface of a sphere, is closed and finite, and would eventually stop expanding and recollapse in a big crunch. A negatively curved universe, like a saddle, is open and infinite, and would expand forever, eventually cooling to near absolute zero. A flat universe sits precisely at the boundary between these fates. Current measurements, combined with dark energy's acceleration, suggest the universe will expand forever, cooling and thinning, but never collapsing. But flatness also relates to the universe's total energy. In a flat universe, the positive energy in matter and radiation is exactly balanced by the negative gravitational potential energy. The total energy might be zero. This has led some physicists to speculate that the universe is the ultimate free lunch, that it emerged from nothing because nothing, properly understood, is unstable. A universe with zero total energy doesn't violate conservation of energy. It simply reorganizes energy from one form to another. Whether the universe is truly, precisely flat or just very nearly flat remains uncertain. Future observations might detect slight curvature. But for now, flatness stands as one of the universe's remarkable properties, a geometric constraint that shapes cosmic evolution and raises questions about why the universe has the particular properties it does. String theory proposes that the fundamental constituents of reality aren't point-like particles, but tiny, vibrating strings. Different vibration patterns correspond to different particles. An electron is one pattern, a quark another, a photon a third. The theory is mathematically elegant and potentially unifies all forces, including gravity, but it comes with a catch. It only works if space has more than 3 dimensions. Depending on the version, string theory requires 10 or 11 dimensions. Where are these extra dimensions? The theory suggests they're curled up, compactified at scales far smaller than we can detect. Imagine a garden hose viewed from a distance. It looks one-dimensional, a line. But get close enough, and you'd see it has a second dimension curled around it. Similarly, string theory proposes that at each point in our familiar 3-dimensional space, there are additional dimensions curled up at scales around 10 or 35 meters, the Planck length. The way these extra dimensions curl up determines the physics we observe. Different compactification geometries produce different sets of particles and forces. This leads to what's called the landscape problem. There might be 10,500 or more ways to curl up the extra dimensions, each producing different physics. Which one describes our universe? We don't know. String theory has been criticized as untestable, more mathematics than physics. It makes few concrete predictions that current experiments can verify, but it remains the leading candidate for a theory of quantum gravity, a framework that might ultimately explain why the universe has the laws it does. Whether string theory is correct or whether nature uses some entirely different approach we haven't imagined, remains one of the great open questions in theoretical physics. The anthropic principle notes a simple but profound fact. We can only observe a universe compatible with our existence. If the physical constants were significantly different, if gravity were stronger, if the electron mass were different, if the cosmological constant had a different value, stars might not form, or chemistry might not allow complex molecules, or the universe might have collapsed or dispersed before life could emerge. We exist, therefore we must find ourselves in a universe capable of producing us. This sounds tautological, and in its weak form, it is. Of course, we observe conditions compatible with our existence, but the strong anthropic principle goes further, suggesting that the universe must have properties that allow consciousness to emerge at some point. This veers into controversial territory, seeming to imply purpose or design, though it doesn't necessarily require either. The anthropic principle becomes more interesting when combined with multiverse ideas. If there are many universes with different properties, then it's unsurprising that we find ourselves in one of the rare universes where life is possible. We couldn't exist in the others, so of course we're here. The apparent fine-tuning of physical constants isn't mysterious. It's selection bias. We observe what we observe because we couldn't observe anything else. Critics argue that the anthropic principle is a cop-out, that it abandons the search for deeper explanations of why constants have their values. Proponents counter that it might be the only explanation available for some features of reality, that not every why question has a deeper answer. It's a philosophical position as much as a scientific one, touching on questions about explanation, purpose, and the limits of scientific understanding. Empty space might not be truly empty. Quantum field theory predicts that vacuum, space with no particles, still contains quantum fluctuations, virtual particles popping into and out of existence, too briefly to violate conservation of energy. These fluctuations have measurable effects. They cause the Casimir effect, where two metal plates close together in vacuum experience an attractive force because the space between them suppresses certain fluctuations. They contribute to the Lamb shift, a tiny difference in hydrogen energy levels. But vacuum energy creates a serious problem. When physicists try to calculate how much energy the quantum vacuum should have, they get an enormous number, something like 10^120 times larger than what observations show. This is the cosmological constant problem, sometimes called the worst prediction in physics. Theory and observation differ by 120 orders of magnitude, a discrepancy so vast it suggests something fundamental is wrong with our understanding. Various solutions have been proposed. Perhaps the vacuum energy contributions from different quantum fields cancel out almost perfectly, leaving only the tiny residual we observe. Perhaps there's some symmetry or principle we don't understand that enforces this cancellation. Perhaps the observed dark energy isn't vacuum energy at all, but something else entirely. None of these solutions are entirely satisfying. The vacuum, that apparently empty space between particles, might be the most important and least understood aspect of reality. It's not nothing. It's a dynamic, fluctuating medium with properties that shape particle behavior and possibly drive cosmic expansion. Understanding the vacuum might be the key to understanding dark energy, quantum gravity, and the ultimate nature of space itself. Time has a direction. We remember the past, but not the future. Eggs break, but don't spontaneously reassemble. Stars shine and cool down rather than gathering energy and growing hotter. This directionality, the arrow of time, seems obvious, but at the fundamental level of physics, most laws work equally well forwards or backwards. You could run the equations in reverse and they'd be equally valid. So where does time's arrow come from? The answer seems to involve entropy, a measure of disorder or randomness. The second law of thermodynamics says that entropy tends to increase in isolated systems. The universe started in a low entropy state at the Big Bang, highly ordered, highly uniform, and has been increasing in entropy ever since. Disorder grows. That's the arrow of time, the reason the future is different from the past. But this raises a deeper question. Why was the early universe in such a low entropy state? Why did it start ordered rather than disordered? A high entropy state is statistically far more likely. Finding the universe in a low entropy state at its beginning is like finding all the air molecules in a room gathered in one corner. Possible, but improbably unlikely unless something arranged them that way. Perhaps inflation provides an answer, creating a smooth, uniform universe from whatever chaotic conditions preceded it. Perhaps there's something about the Big Bang itself that necessitates low initial entropy. Or perhaps we need to think more carefully about what entropy means in a gravitational context, where matter clumping into stars and black holes represents increasing entropy rather than decreasing it. The arrow of time, something we experience constantly, emerges from statistical mechanics and cosmology in ways we're still working to fully understand. The cosmological constant problem is a profound mismatch between theory and observation. When physicists calculate the vacuum energy density using quantum field theory, they get a value about 10^120 times larger than the observed value of dark energy. To put that in perspective, if your prediction was off by a factor of 10^120, it would be like predicting a grain of sand and getting something the size of the observable universe. It's spectacularly wrong. This enormous discrepancy suggests that something fundamental is missing from our understanding. Either quantum field theory's predictions about vacuum energy are wrong, or there's some mechanism that nearly, but not perfectly, cancels out the vacuum energy, leaving only the tiny residual we observe as dark energy. But what mechanism? And why would it cancel to such extraordinary precision, leaving exactly the small value we observe rather than zero? Some physicists think the answer involves supersymmetry, a proposed symmetry between matter and force particles that could cause vacuum energy contributions to cancel. But supersymmetry hasn't been detected at particle accelerators, and if it exists, it's broken, which means the cancellation wouldn't be perfect. Others think the answer involves string theory's landscape, with different vacuum states having different cosmological constants, and we happen to live in one with a small value. Still others think we need entirely new physics. The cosmological constant problem is sometimes described as the biggest embarrassment in theoretical physics. It represents a fundamental failure of our best theories to match reality. Yet those same theories work extraordinarily well for everything else they predict. This suggests we're missing something crucial, some piece of the puzzle that would make everything fit together. Finding that missing piece is one of theoretical physics' greatest challenges. We don't know if the universe is infinite or just extremely large, but bounded. The observable universe, the region we can see, is finite, about 93 billion light-years across. But the total universe could be much larger, possibly infinite. If it's finite, what's beyond the edge? The question doesn't quite make sense because there is no edge, no boundary to cross. A finite universe would curve back on itself, like the surface of a sphere. finite but without boundaries. Different measurements and theoretical considerations point in different directions. The universe's observed flatness suggests it might be infinite, because a finite universe would need to be precisely curved, and observations show curvature is zero or very close to it. But flatness doesn't prove infinity. A finite universe could be so large that its curvature is undetectable within our observable region. If the universe is finite, you might wonder, if you traveled far enough in one direction, would you eventually return to where you started, like circumnavigating a globe? Possibly, but the expansion of space means you'd never actually complete the journey. New space would be created faster than you could cross it. In an expanding universe, even a finite cosmos can be effectively infinite from the perspective of any observer within it. The question of the universe's total size and shape might be fundamentally unanswerable. We're limited to observations within our cosmic horizon. Beyond that lies space we'll never see, never interact with, never know anything about. The universe might extend infinitely beyond our view, containing infinite matter and infinite galaxies, or it might be finite, curving back on itself in dimensions we can't perceive. We know our corner of the cosmos, but the whole story remains tantalizingly out of reach. The many worlds interpretation of quantum mechanics proposes something that sounds like science fiction. Every quantum measurement creates branching parallel universes. When a particle in superposition is measured, rather than randomly collapsing into one state, both outcomes occur, but in different branches of reality. The universe splits, with one version of you observing one outcome and another version observing the other. This interpretation eliminates the measurement problem. There's no mysterious collapse of the wave function, just continuous branching. It's deterministic. Everything that can happen does happen, somewhere in the multiverse of branches. But it comes at a steep ontological price. It requires accepting that countless parallel versions of reality exist, with countless versions of you experiencing every possible outcome of every quantum event. Is this true? We have no way to test it directly because we can't communicate with other branches. Many worlds makes the same predictions for observable outcomes as other interpretations. That's why it's an interpretation rather than a different theory. The differences are philosophical, about what's really happening versus what we observe. Some physicists find many worlds appealing for its simplicity and determinism. Others find it wastefully extravagant. Occam's razor suggests we shouldn't multiply entities beyond necessity, and infinite branching universes seem like quite a multiplication. The debate continues, unlikely to be resolved without new physics or a deeper understanding of quantum mechanics foundations. In the meantime, the many worlds interpretation remains one of several ways to think about quantum reality, each with its own philosophical implications about the nature of existence and observation. Despite everything we've learned about the universe, its age, its size, its composition, the laws that govern it, we've likely only scratched the surface of cosmic mysteries. Every answer science provides tends to generate new questions, often more profound than the ones we started with. We understand so much more than previous generations, yet we're acutely aware of how much remains unknown. Future discoveries may reveal concepts we can't yet imagine. 100 years ago, we didn't know about expanding space, dark matter, or quantum entanglement. 100 years from now, physicists might look back at our current understanding as charmingly incomplete, missing crucial insights that seem obvious in retrospect. Perhaps we'll solve the dark energy mystery. Perhaps we'll detect life on other worlds. Perhaps we'll develop theories that unify quantum mechanics and gravity, or discover new forces and particles that transform our cosmic picture. Or perhaps some mysteries will remain forever unsolvable. Perhaps there are questions we can ask but never answer. Limits to what conscious beings embedded in the universe can understand about the universe itself. Perhaps some truths lie beyond the reach of observation and experiment, accessible only to mathematics or philosophy, or not at all. But this uncertainty is part of science's beauty. We explore, we discover, we revise our understanding, and we continue forward. Each generation adds to humanity's collective knowledge, building on what came before, leaving new puzzles for those who follow. The universe is vast and strange and wonderful, and our journey of discovery, your journey, if you choose to be curious about such things, has no true end. Only new beginnings, new questions, new wonders waiting to be understood. And so we come to the end of our journey through 100 facts about space, 100 stepping stones across the cosmic landscape, from the familiar planets of our solar system to the edges of the observable universe, from the certain to the speculative, from what we know to what we're still struggling to understand. Perhaps some of these facts surprised you. Perhaps others confirmed things you'd suspected or half remembered. Maybe a few sparked questions of your own, curiosities about the universe that we didn't fully address. That's good. That's what these journeys are for. Not just to inform, but to inspire wonder, to remind us that we live in a cosmos far stranger and more magnificent than everyday life suggests. The universe is old. It's vast. It operates by rules that sometimes defy intuition, creating phenomena that seem impossible until we understand the physics underlying them. And yet here we are, conscious beings on a small planet, able to understand something of how it all works. We can trace the universe's history back to its first moments. We can predict its distant future. We've learned the composition of stars, the ages of galaxies, the mechanisms that govern everything from atoms to superclusters. It's worth stepping back occasionally and appreciating how remarkable this is. Every fact we discuss tonight represents years, sometimes centuries, of human effort. Observations, theories, experiments, failures, and eventual breakthroughs. The knowledge we have is hard-won, built by countless scientists asking questions, testing ideas, refining our understanding bit by bit. And the exploration continues. Tomorrow, telescopes will gather new data. Experiments will produce new results. Theorists will propose new ideas. Somewhere, right now, there's a discovery waiting to be made, an observation that will surprise us, a measurement that will force us to revise our models. The universe keeps teaching us, if we're willing to listen and look. So rest now. Let these wonders settle in your mind, like stars settling into their patterns across the night sky. The cosmos will still be there tomorrow, vast and patient, waiting for us to learn more of its secrets. And perhaps in your dreams, you'll wander among those stars, exploring worlds we've discussed, or worlds we haven't yet discovered, or worlds that exist only in imagination. Thank you for joining me on this journey. Until next time, may your nights be peaceful, your dreams be gentle, and your sense of wonder never fade. Good night.